You're listening to WCAT Radio, your home for authentic Catholic programming.
Good afternoon, everyone. Welcome to our iTest webinar, Do You Want to Be Genetically Engineered? I'm Tom Sheehan, Director of the Institute for Theological Encounter with Science and Technology, or just iTest for short. We're very happy to have you, all of you here in attendance, and we hope you will find that this is a very valuable learning experience. We want to open this conference with a prayer. And for that, I'm going to call upon Sister Carla Mae Streeter from the Aquinas Institute in St. Louis.
Welcome, everybody. So just a quick moment of quiet and remembering that we are like fish in a sea of the divine. Whether we know it or not, we float in that presence. Most Holy One, we are most wonderfully made. Coming from your mercy, you have bonded yourself with our own DNA. So precious is it to you. In your gracious kindness, breathe your spirit here, so that whatever we explore, whatever we learn of your truth, may be used by us to give you great joy toward healing and toward the glory of your holy name. We ask this in return for your gracious kindness. And so we ask this blessing for this time together for the glory of your most holy name. Amen.
Thank you very much, Sister Streeter. Now, many of you participating today may be new to iTest, and so I'll give you just a bit of background. The Institute for Theological Encounter with Science and Technology has been in existence for over 50 years. And it's composed of members from all professions, not just scientists. We have theologians, lawyers, teachers, and so on, drawn together by our shared commitment to the principle that faith and science are not opposed, but are partners in searching towards better knowledge of God and His creation. Over that half century, we have conducted many conferences, usually in meeting rooms in St. Louis, which is our physical home. The purpose is always to examine advances in science and pay attention to what they mean for the Christian faith. That goal is common to all of our conferences. We say that iTest explores, as contrasted to giving some final answer. Our website is www.faithscience.org. We invite you to visit there. With modern electronic communications, we've been able to shift to the format of webinars, just in time for this very anomalous year of 2020. This is our fourth webinar in 2020, but it's the biggest and most significant one, dealing with the topic of genetic engineering. We're pleased to have a number of excellent organizations joining us in sponsoring this event. The Department of Medical Ethics in the School of Medicine of Creighton University, the Office of Consecrated Life of the Archdiocese of St. Louis, the Society of Catholic Scientists, En route Books and Media, the St. Louis Guild of the Catholic Medical Association, WCAT Radio, and the Liberty Institute for Faith and Ethics. In particular, Father Tom Davis is head of that Liberty Institute, and I'd like to invite him to say a few words.
Thank you, Tom. I hope I'm actually visible there. There we go. I'm still learning the details of Zoom technology, but it's a pleasure to be here today. The Liberty Institute for Faith and Ethics is a bioethics institute. It has within it the St. John Paul II Bioethics Center, also the Religious Liberty Observatory, and several other resources available, especially a library on bioethical issues, covering a wide range of issues. We've been interested in these matters for a very long time. And all I really want to say today is welcome to all who are coming on to watch this. You're about to experience an incredible, knowledgeable panel. Father Kevin Fitzgerald and I had the pleasure of a conversation last week. It was incredibly enlightening. Richard Dorflinger, I mean, you can't have a more knowledgeable, profound voice on the issues we're confronting across a wide spectrum of matters, especially on matters reflecting in legislation and law, where he's been the outstanding voice for many years for the U.S. Conference of Catholic Bishops in testimony before the United States Congress. And of course, Tim Hunt will be presenting very enlightening, informative information on the regulatory framework and clinical research that's going on in the world of genetic engineering. So thank you for coming and joining us today. I'm very pleased, and the Liberty Institute for Faith and Ethics, Life, is very interested, very pleased to be able to co-sponsor this event. And God bless you all.
Okay, thank you very much, Father Tom. Now, a little bit of instruction here before we get underway. I want to explain the procedure by which we'll handle questions and answers today. At the bottom of your screen are two icons, one for chat and one for Q&A. When someone types something into the chat room, it can be seen over on the right by all attendees, and perhaps others will reply. That is essentially an offline feature of Zoom. Anytime during a presentation to pose a question for the speaker, just type your question click on the Q&A box and then type your question there. All those questions will be reviewed and prioritized for the speaker to respond to. You can help prioritize questions by clicking on the thumbs up icon next to any question that you are interested in. We're going to cover as many questions as time permits. Now, we decided to switch the order of presentations from what we originally had posted in the flyer about the conference. Father Kevin Fitzgerald will be first, followed by Tim Hunt, and then Richard Dorflinger will be third. This will give us a better flow from the basic science to the applications to the ethical considerations. And now it's my pleasure and honor to introduce my good friend of many years, Father Kevin Fitzgerald. Father Fitzgerald, Kevin T. Fitzgerald, S.J., Ph.D., is the John Creighton University Professor and Chair of the Department of Medical Humanities in the School of Medicine at Creighton University. He received a Ph.D. in molecular genetics and a Ph.D. in bioethics from Georgetown University. Father Fitzgerald is an expert on human genetic engineering, cloning, stem cell research, and personalized medicine. He's a founding member of Do No Harm, a member of the Ethics Committee for the March of Dimes, and chairman of several other ethics advisory councils. In addition, Father Fitzgerald has been a corresponding member of the Pontifical Academy of Life since 2005, and now heads its working group on genomics. Also, since 2014, he is a consultant to the Pontifical Council for Culture. His research efforts focus on the utilization of reflection in medical education, on the investigation of abnormal gene expression in cancer, and on ethical issues in biomedical research and medical genomics. He's published educational, scientific, and ethical articles in peer-reviewed journals, books, and in the popular press. Most important to us, Father Kevin has been an absolute cornerstone of iTest for over 3 decades. He is our leading scientist on all aspects of the life sciences, and we've called upon him several times in previous years to organize and lead iTest conferences for our members. 2 such examples in the past decade were early life issues in 2012 and end of life issues in 2016. Kevin first brought the advances in genetic engineering to our attention in 2017, and it is his expertise and leadership that has made today's webinar possible. I give you Father Kevin Fitzgerald.
Thank you. Thank you very much, Tom. And thank all of you for joining us today for this, what I hope will be, and I'm pretty sure will be, a fascinating discussion about what lies ahead for us in terms of the applications of this amazing technology. So I see it as my job today is to sort of introduce you to both the technology and then some of the moral issues that it raises. After I give that sort of introductory presentation, Tim Hunt, who is as plugged in as they come when it comes to what's going on in biotechnology today, will bring you up to date on that. So the more specific information about the actual genetic interventions that are being pursued in clinical research will come from Tim. And then, as you heard, Richard will sort of wrap it all up for us toward the end. So what I'd like to do now is jump in to my talk on, do you want to be genetically engineered? So this is an interesting question, and probably one that many of you never thought you'd be asked during the course of your lifetime. But here we are, because now we are confronted with the possibility of being able to do this in a way that would be accessible to many and have a higher chance of success than what perhaps was thought possible before. In part, what I'd like to do is begin by kind of giving you an idea of the scope of what we're talking about and some of the terminology. So you've probably all seen and heard genetics before, and because of a lot of what's been going on in genetic technology, the word genomics has started to be used a lot more, in part in response to the Human Genome Project, which started in the early 90s, where the idea was to sequence the entire DNA of a human being, or many human beings, in fact, because we all have slightly different DNA sequences. And so nowadays, when we use these terms, we tend to use genetics to talk about a specific gene or a specific family of genes, or maybe some genes that interact with one another. And genomics is used when we're discussing an individual's entire genetic package. All of the genes, all of the DNA that helps regulate the genes, everything that's in all their cells. That would be your genome. And then we can talk about the genomes of many different people. Now, another interesting term that has popped up recently is something we were not quite as aware of as we thought until about 20 years ago. And this is now what we're calling epigenetics and epigenomics. And really, what the Human Genome Project gave us in terms of insight was not so much the book of life that we thought it was going to be, but much, much more how complex that book is. And what we discovered was, yes, you can have a particular genetic sequence, but that does not necessarily define who you are. Because just like in any book, you may have all the words of the book, but if you can't open the book to a particular page, it doesn't really matter what's read on that page or what's written on that page because you can't read it. So epigenetics and epigenomics talk about the regulation of the genes that you have in your genome, how they get turned on and off, when they get turned on and off, in what tissues they get turned on and off, because that is how our tissues are different. All our different cells in our different tissues, except for a few, have the same genome. So how is it those cells do different things and those tissues do different things? It's because of epigenetics. What genes are turned on in those cells and which ones aren't, and to what extent. So that is now an area that has become an extremely important area of research and also now even potentially application. And so what all this comes together is now the use of a technology that allows us to edit our genomes. And what do we mean by that? Well, here is something that you can see comes from the National Institutes of Health and the National Library of Medicine. And this is how they answer that question, particularly in terms of our most recent type of genetic editing, what we call CRISPR. And CRISPR-Cas9 is the first combination of proteins that we applied, but now there are many, many more partners, other Cas proteins like 13 and others that go along with CRISPR to make it even more applicable. So what are we talking about? Well, genome editing, or as you can see also called gene editing, are all these different technologies we use to change the DNA that we find in cells of any living organism. So genetic material can be put in, can be taken out, can be spelled differently, or you can change large pieces. And over the past several decades, many different approaches to this type of editing have been developed. In fact, Tim Hunt will talk a little bit more about that. But the interesting thing is, recently, and as you know how important this is, a Nobel Prize was recently given for this, we discovered a system called CRISPR-Cas9. Now, many people hear this CRISPR, and they wonder, what the heck does that stand for? Well, here it is. Clustered, regularly interspaced, short palindromic repeats. All right, that doesn't help at all. But really, what it's trying to say is, this technology was discovered in bacteria. And it was discovered by the ways bacteria try to fight off viruses that attack them. The way they did it would be to take a piece of the virus that attacked them and then try to keep that in memory in case they were able to survive the initial viral attack. So that little piece of the virus they would keep and put in their own genome. And it was put in a special place in their genome. So it was clustered together. It was regularly interspaced, so you'd have different viral pieces that had been kept as a memory. Palindromic is just that word we use when we have a phrase that is the mirror image of itself, like Madam I am. Spelled backwards is Madam I am. All right, so that's the idea of those. Or is that Adam I am? Sorry. In any case, the idea here is that's how the bacteria structured it so that if a virus came along again and attacked them a second time, they could take that little piece of viral DNA and use it as a template to build a defense against the new attack. And they helped do that with another protein called Cas9. The beauty of this was, as in so many of our other technologies we have borrowed from other species for our ability to edit genomes, even in ourselves, this technology was very interesting because it worked more quickly, it was cheaper to do, it was actually better at the editing process, and it was more efficient than anything that had come before. And so all the technical and financial challenges that we had been facing appeared now to be greatly reduced. And so people got very excited about this, thinking, wow, there are all kinds of things we can do. However, one has to keep in mind that even with this wonderful new technology, things are not perfect. When you are looking to change something in a genome, you have this particular target that you want to hit. But what happens if you hit something else instead? What we call off-target edits. Think of it this way. Genome editing is not unlike your word editing software. And when you want to edit words, what you do is you say, I want to take this particular phrase, let's say, assist breathing, and make sure that I spelled it right, or maybe I know I spelled it wrong, or I put in the wrong word and I want to change it. So you would say find, and let's say you had put in assist breathing, and you wanted to change all of that back to assist breathing. You would type in assist breathing, you would target it, and you would change it to assist breathing. So if we knew someone had a gene that was misspelled, say assist breathing, you would say, well, let's do what we would do in our word processing. Let's target that. We know what the mistake is, so we'll target that, and we'll change breathing to breathing. That's basically what we're trying to do in genome editing. Now, the problem can be that you don't always hit exactly the target you're aiming at. And that's because the way it gets targeted in genome editing isn't quite the way it gets targeted in your word processing software. We look for enough letters to be able to try to give us a precise target. But the molecules, the proteins, don't always work as precisely as we would like. So perhaps what happens is, instead of seeing assist breathing, which we know is a mistake, your targeting mechanism identifies assist branching instead. That's in a totally different gene. That might be in a gene that helps your nerves to branch and connect to other nerves. But the technology doesn't know that. It sees what it thinks is the target and changes assist branching to assist breathing. Well, for that gene, that's terrible. That's bad because now it won't function properly. So even if you were able to, say, fix the cystic fibrosis gene you're trying to correct, which is mutated to assist breathing, and change it to assist breathing, so now the breathing works better. Instead, you've changed a gene that's involved in nerve branching, and you've messed that up. So you might improve the breathing, but you've harmed your brain. This is the problem. How do we balance these things off? How do you know that even if you get 100% of the correct changes that you want, and you get 1% of ones that you don't want, is that going to be worth it? And how are we going to be able to predict what those off-target events may be? So we have to ask ourselves, when we go to use this technology, what's worth it in terms of risk and benefit? What's worth it in terms of improvement to a person's health versus the risks to that help? And of course, some people are saying, well, since we can do things we never thought we could do before, why don't we do things to ourselves we couldn't do before? Not just return ourselves to health, but make ourselves better. Well, what's better? That's a very interesting question. So many people may say, wow, I've always wanted to have perfect pitch. I've wanted to get into music, and I really can't carry a tune, but if I had perfect pitch, wow, I could really do that. And so you say, I could enhance my hearing in my brain so I can have perfect pitch. And in fact, we know areas of the brain that are involved in perfect pitch. Question is, have you talked to people who have perfect pitch? Because some of them will tell you that life with that gift is not always so wonderful. Because if you have perfect pitch, then you can tell when sounds are off pitch, which can be disconcerting. And even from what I understand, because I don't have perfect pitch, can be painful. So it's like going through life always hearing people scratching their nails down the chalkboard. So now, do you really want it or not? Or people who have photographic memories, remember everything. Right? Ask a student, do you want a photographic memory? Guaranteed almost they're going to say yes. Until you talk to someone with a photographic memory and ask them, what is it like? Well, one of the difficulties I understand is at times it can be difficult to remember when you remembered something because everything is so clear. And so it's hard to get a temporal sense of things, like many of us may just consider to be natural. So when we're talking about the targets for these things, how do we discuss that? How do we frame that issue in terms of what we think we should do and shouldn't do? Should we try to enhance our health? In a sense, we already do enhance our health. We're talking about that a lot these days when we're talking about vaccines. You don't give vaccines to somebody who's sick. You give vaccines to somebody to prevent them from becoming ill. That, in a sense, is an enhancement of our immune system. We don't have any problems with that enhancement. We might have much greater problems with other kinds of pursuits of enhancement because it's not so clear what the benefit is and what the risks are. So maybe we should just look at this in terms of saying, we're just going to protect our health. We'll use it just to return people to health. How do we frame that discussion? Traditionally, it was often considered to be sort of two axes upon which one should make some of these decisions. Was what you're going to attempt to do considered therapeutic? In other words, with like cystic fibrosis, the person has a mutation that we know is causing a particular protein not to function the way it's supposed to, which leads to the problems of the disease. Now, going in and genetically changing that, one could say, okay, that is strictly therapeutic. Again, vaccines are also broadly accepted in our healthcare system, and yet in a way those are an enhancement. So many people now are a little concerned about that distinction between therapy and enhancement because it's not always clear what that is. If a person is anemic, don't have enough red blood cells to carry oxygen appropriately in their body, you would say that they are ill and that they should get extra red blood cells to address their anemia. But what about a person who is about to go run a marathon? And they say, well, I want to run a marathon, but the number of red blood cells I normally have isn't going to allow me to perform at my highest level of function. So why shouldn't I get more red blood cells? Is that an enhancement? In sports, it's called blood doping, and it is considered an enhancement. But when astronauts go into outer space, they too can run into problems with their bone marrow producing enough red blood cells. Is giving them extra red blood cells therapy or an enhancement? So these are kinds of the conceptual struggles we're going to have with that particular distinction. The other distinction is a little more clear and easy to make. That's the distinction between cells in your body that are just yours. They're not going to get passed on to the next generation. Those are called somatic cells. Cells that do get passed on to the next generation because they are the beginning of the next generation, sperm and egg. And the cells that produce the sperm and egg are called germline cells. So here the question is this: if you do a genetic edit, is it okay if it gets into the germline and gets passed on to the next generation? Some people would say not only is it okay, it's obligatory. Because if you're going to do something for the parent that the parent needs and correct a genetic mistake that's in the parent's body, then of course you should do that for any offspring. But again, remember, this is complicated. When you change something, you might have off-target impacts that you don't know about until they show up in the next generation. Or you might even change something and say to yourself, see, I just fixed this. But in that particular genome, having changed that changes other things. So germline genomic engineering, as again you will hear later, is something that is considered much, much more fraught with all kinds of moral and ethical problems. And right now is not something that is seen as ethical to pursue, although we will talk about one instance in just a minute. So currently, and as Tim Hunt will fill in much more detail, somatic cell, so one person's own body, the cells in one's own body, therapeutic, something that is obviously targeting a disease, is thought to be where we should be looking at using this new CRISPR-Cas9 technology if, again, we can show it's safe enough to do in terms of that risk of off-target effects versus the benefits we're trying to achieve. So that brings us back to then, well then, what will we say is genomic health? How can we determine if something is in fact contributing to genomic health? How do we delineate it? Who's healthy and who decides who is healthy? How are we going to wrestle with those questions? So for instance, there's wrestling that already goes on in this area. Many of you may be well aware of the deaf community, and I've had opportunity to work with two institutions, both Gallaudet University in Washington, D.C., which is a university for the deaf and the significantly hard of hearing, and in Rochester, the National Technological Institute for the Deaf. Both of those institutions are focused on people who struggle with hearing loss. Now, the issue that comes up, which is again a very interesting conceptual issue, is deafness a disease, or is it a difference among human beings? Because the members of the deaf community who have learned how to accommodate themselves to their lack of hearing will say that their accommodations in fact have created a culture that has many significant characteristics that make that culture in fact worth retaining, worth preserving, and maybe even worth expanding. And what do they mean by that? Well, in my experiences in Washington, D.C., when I was at Georgetown University, you could go on the public transportation and you would see groups of people who would be gathered together, having a great time, signing with each other. And they were out as a group because they knew that their lack of hearing made moving around in the city a little more dangerous for them than for those of us who can hear. And so their obvious acceptance and embrace of their interdependence upon one another was actually an example of something that in many human cultures we value. That idea that we can't go it alone, that we need each other, that we need one another. And so the idea there, they would argue, is this is actually something you don't want to get rid of, deafness, because one of the consequences will be losing this culture. The other thing I want you to struggle with a little bit is also recognizing the fact that as a geneticist, I can tell you all of us have mutations in our genome that make us different. All you have to do is look around. The question is, again, the same question that the deaf community wrestles with. Is it a difference or a disease? And how do we draw those lines? So since I said all of us have that, I guess I should focus on myself as an example. And actually, that's not difficult to do. Because even though now you cannot tell it because the fires have gone out up there, here is a picture from 20 years ago. And those who have known me for decades can certainly confirm the fact that, yes, I am a ginger. I am a redhead. Or, as we say in genetics, a melanoccortin-1 receptor mutant. So my protein, the melanoccortin-1 receptor, which is important in terms of skin color and hair color, including some other things, as you will hear, is different than most people. In fact, different from a lot of people. People with this particular mutation are thought to account for maybe 1% to 2% of the population in the entire world. So we are a minority, right? And being a mutant, as many of you know from sci-fi movies, we have both our superpowers and our weaknesses. The superpower actually is kind of interesting at the moment because one of our superpowers is, where did red hair come from? Primarily it's thought in the northern British Isles, so Scotland and Ireland and other isles from around there. Why? because it's cloudy there. You don't see the sun very often. So you don't have to worry about the sun. What you have to worry about is making vitamin D. And having this mutation allows redheads to make their own vitamin D, much more so than anyone else. So that's interesting today as a superpower, because one of the things we've discovered is if a person has a vitamin D deficiency and gets COVID-19, that person is at much higher risk for significant detriment from the disease, for getting a severe reaction, from having severe problems. So having good vitamin D production turns out to be a great thing. Now, of course, we redheads also have to have our weaknesses, right? Our Achilles heel. And of course, all you have to do is think back from where redheads, we think, come from. And those are those cloudy islands. And so if you look at this, you will notice that this is well known, right? If you have red hair and freckles, you have a much higher risk of getting, in particular, melanoma. We don't do well in that bright sun. So that's why redheads often have to have a lot of work done on their skin if they've been out in the sun, because we have to be careful of that mutation. Now, the question is, if we're going to do genomic editing, right, is having red hair a good thing or a bad thing? I mean, if our climate does change significantly and for some reason we cloud over the earth, then my people are going to do very well. On the other hand, if we blow away our ozone layer, we're going to be the first ones to go. So a lot depends on the environment, the context. And that's why diversity is such an important thing in a species, genetic diversity, because it keeps the species healthy. Now, interesting, again, some of that genetic diversity can raise some interesting questions. And those interesting questions can lead to very interesting problems. So many of you may be aware of this scandal. As you can see, this was late in 2018. And this is, I believe it's pronounced Dr. Ha. It looks like he, but they pronounce it Ha. And Dr. Ha used this CRISPR-Cas9 to try and genetically engineer 2 baby girls so that they would be resistant, naturally resistant to HIV. We have discovered that there are people in the world that have a particular mutation. You can see it there, the CCR5 mutation, which protects against HIV infection. So they're basically immune to HIV infection. And he thought, I'll use this technology to genetically engineer these 2 girls so they will grow up immune to HIV. And the reason he did that is because one of their parents had HIV. Now, again, remember the off-targeting problem I told you about. Well, we have not solved that. So, in fact, preliminary data seem to indicate that Dr. Ha didn't exactly achieve the good benefit he was trying to get and may have caused some other problems for these 2 little girls. This raised enormous ethical controversy and problems. Now, another issue, of course, that didn't seem to be taken into consideration by Dr. Ha is the fact that, yes, the CCR5 mutation does make you resistant to HIV, but it makes you more susceptible to other types of infections. So you always have to remember, when you make a change, we are complex organisms. And how do you balance that out? So in response to this particular scandal, an organized committee for this summit where Dr. Ha did his presentation, as you can see, it was the Human Genome Editing second conference. They came out and said, even if it had worked, which it didn't appear to, the procedure was irresponsible and failed to conform with international norms. And this organizing committee for this event, so a lot of different scientists and some ethicists, said, what we really need here is an international forum, an ongoing internet. We're going to have to discuss this for a long time because new technologies will arise. And we have to foster broad public dialogue, which means everybody, and to develop strategies. Because even if we're able to do this, are we going to be able to say that it will be available to everybody? Or will this technology be another way in which we are going to create greater health inequalities in our systems around the world? So the goal, as said by this particular organization, but certainly a goal that is very much embraced within the Christian tradition, is this going to meet the needs of underserved populations, of the people who need it most? So how do we go forward with all of these questions in front of us? How do we get good genomic editing done? One way, of course, is to ask ourselves, what are, in fact, the goods we're trying to achieve? What are our goals for using gene editing on human beings? And in order to understand that, we are going to need to hear from everybody, in particular, the underserved and the marginalized, because their voices are the ones we most often do not hear. If we do this, some people complain that, well, you'll slow the process down of the technological development. And I will agree, that is true. This probably will slow it down. But what's the goal? Is the goal mere technological development and advance? Or is the goal, even as that committee said, figuring out how to care for those who are most in need? So which goal do we want? Better technology or better health care? With the emphasis on caring for one another. So I'd like to end with a South African phrase, which I like very much, which says, if you want to go fast, go alone. If you want to go far, go together. And that is the question I leave you with. Do you want to go fast? Do you want to go far? Do you want to go by yourself? Do you want to bring everybody along? So I thank you very much for your attention, and I look forward to any questions or comments you may have.
Okay, thank you very much.
There we go.
We appreciate your presentation. Now, I want to introduce everyone to our conference manager, Sheila Roth, in our iTest headquarters in St. Louis. Sheila will conduct the question and answer session.
Okay, thank you, Tom, and thank you, Father Kevin. It's an excellent presentation. We don't have any questions posted in the Q&A as of yet, so please feel free to type them in the Q&A section at the bottom of your screen. I had a question about Dr. Huh.
Yes.
And you talked about if you want to go fast, go alone. So I guess he would be the example of that. Wasn't he kind of on his own and, well, pretty much didn't tell the global community what he was doing? Is that correct?
Well, that's a very good, actually, it's an excellent question. The fact of the matter is, I mean, he knew that what he was thinking of doing was going to be very controversial. So he did, in fact, contact some people, both scientists and ethicists, ahead of time to ask them what they thought of trying to go down this road. I don't think he was extremely open to sharing details about what he was going to do, but I think everybody got the idea of what he was trying to attempt. And my understanding is, across the board, people were saying to him, no, it's too soon, we shouldn't go there. But what also came up was others who were not privy to those conversations, raising the question to those who were involved in those conversations, why did you not warn the rest of us that he was thinking of doing this? And one of the responses that was most often heard was, well, when we told him not to, we didn't think he would. And that's a really interesting question. What do we have in place? And Tim Hunt will talk a little bit more about this in specific, but what do we have in place to try to prevent these kinds of efforts? Now, the interesting other aspect of this is, of course, it took place in China. And the question is, did the Chinese government know about it? And many people who are familiar with the Chinese government and the way of doing things in China presume that somebody knew. So the question was then, what happened after this occurred was that the Chinese government said that Dr. He had violated all kinds of restrictions and norms and problems, and I believe he is still under house arrest in China for what he did. But is that sufficient prevention, protection in China? And is China unique in terms of the fact that somebody could actually marshal the resources and the expertise and the patience to actually do this kind of procedure? So other places in the world where there's concern about what this might happen would be places where there'd be weaker restrictions or weaker government oversight. So there might be restrictions on the books, but the government has no way of really enforcing them. And that then raises the question of, should there be some kind of global regulation? Could there be a global moratorium? And if so, how would that be enforced? Because this technology, one of the amazing things of CRISPR and all the different ways it's being developed, is you can go online now and buy a CRISPR kit to take to your basement or garage and do your own experiments on the bacteria that come along with the kit. That's how easy it is to use. And so it's no longer the case that you can say that this technology is protected because it's in government labs that have all kinds of security and only the handful of experts can do it. Nope. That genie is out of the bottle. This kind of technology is something that doesn't take a lot of expertise and skill to attempt. To do well and to achieve, oh yes, but not just to attempt, as Dr. He proved.
Very good, very good. Thank you. Oh, we have a lot of questions now. Remember, you can vote on questions that you think might be more, you might want to move up to the top of the list. So I'll just read one. If they believe they could come up with the idea of gene editing, could they potentially use gene editing for people for whom cancer runs in their family?
Yes. In fact, that's a very good question. Depends. Again, this is a complex issue, right? So obviously, I'm one of those people in a sense, right? At being a redhead, I'm at higher risk for melanoma. Should we go in and change the mutation, right, for future generations so we don't have redheads anymore? Well, I don't know. I think the world would be a much worse place off without redheads, but I'm a little biased. So are there mutations that we know, and there are many of them, that lead to an increased risk for cancer? Now, here's the interesting question. Are those mutations that lead to cancer in one particular type of tissue, say breast tissue or prostate cancer? Or are they a kind of mutation that results in tumors in many different types of tissues, which is called, one would be, for instance, Li-Fraumeni. So Li-Fraumeni is a mutation that knocks out a gene which helps cells self-destruct when they are in the process of becoming cancerous, or helps them fix the problems. And when that particular break or defense is gone, those people who have that particular condition can develop cancers in a variety of tissues. The reason I bring up that distinction is, if you're going for one that may only express in one particular type of tissue or cell, you have a much higher chance of being successful because you don't have to hit all the cells of the body. But if you're going for a mutation that can cause problems in all the cells of the body, then that's much, much more difficult to be successful. Now, you could say it'd be worth just reducing the risk by fixing the mutation in a significant percentage of cells. That could be the case. On the other hand, again, the more you change, at least currently, with the technologies we have, we still have to worry about those off-target effects. The question here is, what's the balance? Would you cause a problem somewhere else that might be worse than the problem you fixed? And how are we going to know that? So right now, that's the big issue that we are facing when we're trying to use genome editing in a preventive way before someone has a disease. It's much easier when someone has a disease in terms of saying they already have it, they're already dying, or they're already suffering greatly. So even if we have an off-target effect, it's going to be difficult for it to be worse than what they already have. But if you don't have cancer yet, and it's just a higher risk, how much do we balance that risk with the risk of the off-target effects and the other kinds of effects that it might cause? So great question, and this is part of the big challenge that's ahead of us in discussing this.
Okay, very good. Thank you. Here's another question. We have mapped the human genome, but does that mean we know all there is to know about what each gene is capable of? In other words, might there be future discoveries of certain genes being recognized as responsible for various superpowers or mutations?
I love the way you framed that. Perfect. I can pretty much guarantee you, yes. There will be lots of discoveries, many of which will be surprising. That, of course, is why we do science, right? If we thought we already knew everything, then why would we need to keep doing research? Because we'd already know everything. So we obviously don't. One of the things I like to remind people is, if you go back to the early 90s, some of the justification for spending the billions of dollars that were spent in pursuing the Human Genome Project was that we were going to get the book of life. I mean, we were going to sequence and we were going to know everything, that there was to know about human beings. Well, the beauty of the Human Genome Project is it showed us that DNA sequencing is not the book of life, and it's not even a great table of contents, because we discovered so many other levels of regulation and interaction that we hadn't really considered before, that was the real benefit of the Human Genome Project. We discovered just how complex we are and just how much it matters that even if you have identical twins, you can change how they look and behave and think because of the environmental effects on them, affecting their epigenetic regulation and expression. So absolutely, I guarantee you that. Now, in terms of superpowers and weaknesses and all that, hey, it all depends on what you're looking for, right? So whatever the future brings, the beauty will be, presumably, we will have our usual wonderfully diverse human population in which some people will discover they have things that are working very well for them, and other people discover they'll have some challenges that they didn't anticipate.
All right, thank you. Going back to CRISPR, here's another question. Instead of creating an international committee to regulate globally, would it not be a more important initial step to regulate the availability of the public at large access to kits such as CRISPR? But then who decides who should be allowed access?
Great, yeah, and that is the issue, right? So one of the questions that comes up is, how would you potentially, right, limit the availability, shall we say, of this particular protein and the other proteins that you would use to work with it, when so many people could make the argument to say, I need to have access to this because I'm in healthcare, I'm in agriculture, I'm in animal husbandry, I'm in whatever, right? And I'm an 8th grade teacher and I need to show my students how this works, right? So that's one of the, again, very interesting conceptual issues that arises when we try to say, how are we going to restrict access to this kind of easy technology? Which then, of course, gets back to, well, then, how do you even consider a regulatory mechanism, or where do you draw lines? Well, one way that one can start to move in that direction is to say, Are we having the discussions? Are we having that broad public engagement that everybody's talking about that we need? Are we actually having that so as to stimulate people's understanding of the dynamics that are in front of them and the different features of this challenge, such that I'm not going to want to do something with this that might harm you or someone else, even though I think it might be fun to do and I think it might even be beneficial for myself. But I'm not going to take the risk because I suddenly become aware of the fact that, oh, I didn't realize how that might harm you or how that might make your situation worse. So that, I think, is a very constructive way we can go forward. Of course, one of the problems, as you can tell, it's been a few years at any rate, and we don't have that global public engagement going on. But there are many people who are looking into that, and one issue I've raised for the Catholic Church is, why are we not taking the forefront on this and saying, look, we are a global organization. We have parishes around the world. We have people around the world. We have representation in every country in the world. So could not we be a place where at least some of that engagement gets started?
Okay, very good. Another question, can hacking with the easily accessible CRISPR kit nefariously affect, say, the food gene pool?
Yeah. So this is, one of the issues that they have to look at. Now, again, here's the dynamic or the feature of this that so far is keeping most people fairly comfortable. You can go in and try whatever hack you want. As we know from genetics, there are a lot of mutations that occur in any living species all the time. The vast majority of those mutations, vast majority of those mutations, right, don't really help the cell do any better, and the cell dies and doesn't replicate, and so the mutation isn't carried on. Or the organism can't develop, and the organism doesn't carry on and create more organisms. The question would be, even if you were trying to create a nefarious mutation, your chances of success are no better than trying to create a very beneficial mutation. Any specific targeting that you're trying to do, right, is going to be difficult to make sure that you achieve without causing any other problem. So far, it is our inability, right, to do this as precisely as we would like all the time that is, in fact, part of our defense. Now, as you will hear, again, when you're trying to treat a person with a disease, you don't necessarily need to have 100% success. In fact, if you can find the cells, say 5% of the cells that you were able to fix correctly, that may be a sufficient number to put back into the patient to allow the patient then to have a much better life. So these are the dynamics that we're wrestling with. But yeah, the beauty right now is the probability of success if you're trying to do something bad is no better than the probability of success if you're trying to do something good.
Yeah. Okay. All right. Let's see. Oh, here's a question. We're talking about how fast things progress. So the question is, how slow is slow? We usually know how fast is fast.
That's a good question. And again, it's all relative, right? So let's think for a second. When were the first serious considerations for the application of genetic engineering on human beings? It was back in the mid-'80s when they were talking about, if some of you remember David the Bubble Boy. There's a boy who had to live in a bubble because his immune system didn't work. So any virus, bacteria, whatever, he would die. He just didn't have a functioning immune system. So the idea was they knew the genetic difference that caused that in David, and could they go in and fix enough of his cells, right, to give him a functioning immune system? And that was back in the mid-'80s. They were having those discussions. We are now in 2020, and only now is this really exploding. Was that slow? Was that fast? I mean, it depends on who you're talking to, right? When you think of all the technological hurdles that had to be cleared, one could say, wow, that went a lot faster than we thought it would. But for others, they thought, wow, we thought it would be easier to do than it turned out to be. So, yeah, and then what's going forward? I'm just going to presume that the technology is going to continue to advance rapidly. The question is going to be, are the technological advances going to be the ones that are going to allow us to do the good we want to do without getting the harms? Are they going to be something else altogether, which again is just going to cause all kinds of confusion and ethical challenge? Don't know.
Okay, great. All right, I think it's time to hand it back over to Tom, and thank you, Father Kevin.
My pleasure.
You can take over now, Tom.
Okay, let's see if we can get my camera on. Okay, the next phase has to do with what's going on out there in the real world. And for that, the key speaker we've chosen today is Tim Hunt. Okay? Tim Hunt is a biotech executive with more than 20 years' experience in the field. He's most recently served as Chief Corporate Affairs Officer of Aditas Medicine, a leading gene editing biotechnology company. While at Aditas, Tim was actively involved with many of the leading policy debates around genetic editing. This work took him to such interesting places as the Vatican, the WHO, and Hong Kong, where he witnessed Dr. Hu's announcement of the world's first genetically modified babies in November 2018. Tim received his JD degree from Catholic University and his BA at Boston College. When not thinking about gene editing, Tim can be found in Hingham, Massachusetts, with his family, which includes his wife Jennifer, 2 teenage children, and his dog Finn. I give you Tim Hunt.
Thank you very much, Tom. I appreciate it, and thanks for inviting me, for organizing this terrific webinar on such an interesting, cool, and I would argue timely topic. My thanks to Sheila as well for all the help and support, and to the whole iTest team, and for Kevin for recruiting me in here initially. I'm going to see if I can successfully navigate the technology and get some slides up. Let's see. I think that should allow people to see my slides. Someone please yell in my direction if that's not the case. So my topic today, kind of building on a lot of the things that Kevin said, is on gene editing, clinical progress, and the kind of regulatory and some of the global governance frameworks that are some that are the regulatory frameworks that are well established, I'll argue, and the global governance frameworks that still are very emergent. But in some ways, the kind of subtopic here could be, it's really gene editing over the last, I would argue, few years. And my strong guess is into the future, is sort of the subplot is kind of a tale of hopes and fears. And that's one of the reasons why I find it such an interesting field. It's a CRISPR gene editing, but the broader field of gene editing, I would argue, really represents a highly disruptive technology that is advancing rapidly. And it kind of evokes these hopes and fears. You think of things like, just even setting aside for a moment the human application, what could you do with gene editing and agricultural applications? A lot of potential hopes, concerns that some people have around, the next wave of GMOs or lightly regulated GMOs, or what could you do to potentially eliminate or reduce malaria transmission from mosquitoes by using gene drives? Other people are concerned, hey, next thing you know, you start monkeying around with the mosquitoes and the birds start falling out of the sky. Or some people say, geez, you could do a lot with animals to make them larger and let them produce more beef or milk or whatever. Others see tricky, difficult sides of that. And in fact, when I was at Editas, one of our scientific founders, George Church from Harvard University, who's one of the best known genetic engineers in probably the history of genetic research and development, has said, hey, I'm going to work on trying to bring back the woolly mammoth, right? So you could see how that gets a lot of people's blood pressure going, bringing back species. So a fascinating field, lots of applications. We'll talk today about human health, but in lots of other fields that make it, I think, fascinating. So with that, Tom also needs to be properly recognized for his excellent timing. So months ago when he set this in motion, it's as if he knew that this week the 2020 Nobel Prize for Chemistry would be awarded to Jennifer Doudna on the right and Emmanuel Charpentier on the left for their pioneering and excellent work back in 2012 on CRISPR gene editing. It's the first time that the Nobel Prize in Chemistry has gone to a woman, or in this case, two women, without being kind of co-shared by a man. So that's been that's gathered a lot of rightly gathered a lot of great praise and attention. Jennifer Doudna was one of the scientific founders at Editas, and she and Emmanuel Charpentier have gone off to found a number of biotechnology companies that are doing some very interesting work in trying to advance human health. So a big congratulations to them, and very timely for us to be celebrating gene editing this week and exploring these topics. So maybe to start, if you think about biotechnology companies, and some people are more familiar with the basics of biotechnology companies and some a little bit less, but they're really built for a purpose. And the purpose, going back, say, 40 years, a little over 40 years in biotechnology, is to take the interesting science that emerged out of the 60s and 70s around recombinant DNA and apply it to trying to alleviate real human suffering, right? So it's to really get after the genetic conditions that drive rare disorders and see if you can actually eliminate human suffering. And it's been a tremendous field. It's an American-built institution and field. And in the United States, we probably have 80-90% of the companies out there, 80% of the companies out there. It's estimated there's something like 6,000 rare diseases that cause genetic mutations. That's a figure from the National Organization of Rare Disorders, the big U.S. patient group that does excellent work. Their estimate is that there's about 1 out of 10 Americans suffer from some form of a rare disorder, and it's believed that on the European basis that somewhere in that realm as well. Shockingly, I think for many of us, only about 5% of these diseases have some kind of FDA or European approved therapy. So again, huge unmet need. And in the case of something like a sickle cell disease, which is seeing a lot of innovation going on with clinical trials right now, which is a terrific thing. There are about 100,000 patients in the United States, about 30 to 50,000 is estimated across Europe, primarily African American in the United States. You end up with deformed and diminished blood cells that cause anemia, pain crises, organ failure, and frequently mortality. They have regular crises, pain crises that end up where they end up in the emergency room. And the average, the median life expectancy is about 45 years. In fact, I think I was with Editas for about 3 years, and I had just heard that someone had died from sickle cell. And I turned to a colleague and I said, I've met 4 patients that have sickle cell, and I think 3 of them have passed away in 3 years. And this was a very, very tragic, a 32-year-old young man who died of a massive stroke. So I think the picture I'm painting is that the way I think of it, for too many of our patients, the status quo from these rare diseases too often represents death or serious disability. So it's kind of the mission of all these biotech companies is to kind of get after that and see what we can do using any of a number of tools and technologies to try to help patients. I'm going to go quickly through a few slides, and a few slides I'll pause and spend more time on. Kevin did an excellent job of kind of ticking you through the basics of gene editing. A way I think about it a little bit is, and Kevin touched on this, gene therapy you hear about sometimes is think about that as it's really sometimes called gene augmentation. You're adding a piece of DNA in an attempt to correct a mutation that leads to a serious or oftentimes life-threatening condition. Gene editing, as Kevin articulated, we sometimes would say an attempt to repair broken genes. Kevin rightly flips it around and says, well, it kind of depends on your perspective. Sometimes, maybe you don't want to fix the redheaded gene because you might have some other cascading events that are a challenge. But it's an attempt to kind of get after DNA, typically using a precise way of cutting DNA to remove, disrupt, replace a mutation that leads to a life-threatening condition. Sometimes it's not cutting DNA. Sometimes it's actually swapping out the chemical letters. But most often, most commonly, it's thought of as actually cutting DNA. And in fact, that's actually, for those of us, myself included, that are not scientists, we don't think about it. But we're sitting here right now watching this really cool webinar, and our DNA is breaking and repairing itself. Breaking and repairing, repairing thousands of times, on and on and on, millions of times. When you're up in an airplane, Kevin was talking about, the sun and the challenges for those afflicted with redheaded disorder like Kevin. When you're up in a plane and you get exposed to more radiation, your DNA breaks and repairs itself at a faster rate, more breaks. If you smoke, you see more breaks. There's lots of things that happen in nature or that we kind of put upon ourselves that can accelerate the breaking and repairing of DNA. But it's interesting because most of us don't think of it. It's actually a naturally occurring event. Gene editing can be in vivo inside the body. It could be a subretinal injection if you're trying to improve someone's vision. It can be through almost like an IV setting, or it can be outside the body, ex vivo, where the cells get extracted, they get edited, they get implanted back into the body to try to correct a condition. That's frequently what you see in things like sickle cell disease. And then depending on what actual specific genetic mutation you are attempting to correct, you might use gene therapy or gene editing. So for example, in one form of blindness, gene therapy works much better. It's a company named Spark Therapeutics got a product approved through the FDA a few years ago. They use gene therapy. The company I worked for, Editas, is doing early work on gene editing. Both are forms of blindness, but one makes sense with gene editing, one with gene therapy, and some of it's got to do with the length of the piece of DNA you would want to insert. Sometimes it's too big to actually get it inside a viral, what's called a viral vector. It's sort of like a delivery device to put in into the body. So depending on what you want, you might use gene therapy, you might use gene editing, depending on what you want to do. There are different forms, different platforms. Kevin alluded to this in biotechnology of gene editing, and they've been around for a few years. It's on the one hand, it's new technology, and on the other hand, it's been around for a while, which is oftentimes the case in biotech. So some of the, I said older, I probably should have said more established or kind of the early forms of gene editing include zinc fingers, meganucleases, and what's known as talons. And the early kind of pioneering work on those were done going back to the 1980s. And in fact, zinc finger clinical trials are very active. We'll talk about that in a moment and seem to be making some excellent progress. The newer technologies are the ones thought of as CRISPR and what's known as homologous recombination. A lot of that work was done kind of in the early 2010s. And of course, I mentioned Jennifer Doudna and Emmanuel Charpentier's pioneering work. And then the kind of latest technologies are what's known as base editing, which is this attempt to swap out the chemical letters without actually cutting DNA, prime editing, and others. And the bigger point here, I think, is on the one hand, the technology has been around for a while. So we'll talk about it in a minute, but there's a fair amount of experience, both sort of on the company side from many of the leading academics and regulators. They are generally pretty comfortable with the technology and how to apply it in a clinical trial setting on the one hand. On the other hand, this field continues to evolve. A lot of the leading academic pioneers they're just continuing to drive new forms of technology. So Feng Zhang, David Liu, both at the Broad Institute, Keith Jung at Mass General. These are some of our founders. They're going off. They founded Editas in 2013. They're coming up with new technologies, founding more companies. It's a very interesting, very dynamic field, which is all for the betterment, frankly, of patients. And you see from some of these photos, these are some of the actual live patients and physicians doing the work in some of the firsts. The photo to the right of the young man with the baseball hat on was a young man that got dosed from a Sangamo clinical trial. Sangamo is a California-based biotech company, really the first kind of company working on gene editing. And back in 2017, they did the first in vivo application of gene editing to this young man. The woman to the left is a sickle cell patient. She received the first dosing of CRISPR gene editing in the United States to try to alleviate her sickle cell disease, and to date it appears as if it's been very successful. She's had very few, I think she's had no crises. And then the bottom photo, this is just back from March, was my old company Editas dosed a patient, or the physicians dosed the patient out in Oregon to try to use CRISPR to alleviate a rare form of blindness. So good progress in these still early days in gene editing. This kind of summarizes when you think of the kind of, a lot of people think there's sort of 4 of the more established larger companies that are out there, larger meaning probably 200, 250 people on the kind of small side and probably more like 400 on the larger side. All these companies have, the 3 kind of bottom companies all work in CRISPR Therapeutics, Editas, and Intellia all work primarily with CRISPR gene editing, and all were formed in 2013. Sangamo goes back about 20 years. But I just listed out, and I won't go through them all, but some of the major clinical trials that are going on right now, right? So Sangamo's working in sickle cell. They're working in this rare disorder, MPS, which this gentleman had on the front page there on the previous slide. CRISPR Therapeutics has got this woman, has got a trial up and running, as I mentioned, for sickle cell and beta thalassemia, and they're doing really good work in cancer as well. Phase 1 clinical trials, but they're moving forward. Editas Medicine has had very good luck with their LCA10 program. The product construct's called Edit 101. It's in phase 1/2 clinical trials. And by the end of the year, they hope to have their what's called IND. It's the significant amount of paperwork and all the data that goes into the FDA to ask for permission to start running human clinical trials. They hope to have all that filed by the end of the year. And Intellia, another excellent company, is working on a rare liver disorder called ATTR. And the theory in a lot of these cases is, you might be able to go in and see a physician once, have a one-time injection, and you may not have what we would think of it as a cure. You may have a durable effect. Maybe your symptoms are dramatically improved or alleviated for 5 years or 10 years. And there will probably be some patients that will, for practical purposes, it may seem like a curative effect that goes on many, many years, perhaps for their life. We were always super sensitive, thinking about the blindness community, about not wanting to overpromise and not run out and say, we're going to cure your child. LCA10, oftentimes the best interventions would take place with younger patients. So teenagers down to maybe 3 years old. Some of these diseases, if you can get them early, you may have a better clinical outcome long term. And we never felt comfortable, frankly, running out and talking to parents and saying, we're going to cure your child from this rare form of blindness. Because frankly, you don't know what exactly you're going to get in these early clinical trials by way of results, right? 1. And 2, really phase 1, phase 2 trials, you're thinking about, can we prove safety? We would like to see some signals of efficacy, but you're not exactly sure what the dose. Maybe you need a slightly higher dose and you need to go back and try it again. There's a lot of learnings that need to take place in these clinical trials. But also, you could perhaps take someone that is blind or can only perceive light and dramatically improve their vision, but that's not a cure. They might not be able to drive a car. But they might be able to see their parents' face for the first time ever. And that would be terrific and a very meaningful intervention, but it wouldn't be a cure. So that may explain for those that are tuning in, how we think about it. We talk about things like you might have a durable effect, and that might be desirable and very clinically meaningful. And when you pan back, so I sort of dove in on 3 of the clinical trials, stepped back and showed all those other clinical trials. And when you scope back on it even further, you see, and this is some months old, but a snapshot in time from a year ago or so, there were about 35 gene editing clinical trials that were up and running in the United States. This was a poll we did out of clinicaltrials.gov to see what was open. And you see many of them are in blood cell disorders, hemoglobinopathies, oncology 16, HIV, HPV 7, ocular was the Editas one, and then there are a few other rare disorders. So a lot of progress. And my guess is, purely a guess, is there's more than 35 today. Okay, so with that, and you think, all right, well, that's all great. Meaningful progress for patients sounds good. Science is moving, sounds good. How is this stuff really regulated? I mean, is it really safe? Is it the Wild West? We hear about Dr. Huh and people like that. But as Kevin kind of grounded us, this is when we talk about the real clinical trial work being done in places like the US and Europe and Japan and a lot of other countries, it is highly, highly regulated. Biotechnology is arguably the most regulated industry in the history of the planet. Probably has got some competition from the airline industry and the nuclear power industry. Heavily, heavily regulated. Doesn't mean there can't be mistakes, and there are, because it's drug discovery and development, which means you're going to probably end up with some mistakes here and there, but enormous care is taken to try to get it right every time. And the good news is we're talking about, again, somatic cell gene editing, right? So these somatic cells are only in cells in people that are walking around, gene editing for therapeutic purposes. And so what you see here is in the United States, there's a robust regulatory framework. It was really built out going back to starting in those early days of recombinant DNA in the 70s, in the early 80s, where both the FDA and, interestingly, the National Institutes of Health asserted jurisdiction over technology. So there's more than 40 years of overall biotech oversight. There's about 30 years of oversight with gene therapy clinical trials, which a lot of people tend to forget. But the gene therapy clinical trials have been going on for a long time, including with some prominent, significant, and meaningful and tragic setbacks. But, the gene therapy field then retrenched and kind of learned how to make better clinical trials, design better clinical trials, run them better, improve the technology, and gene editing has benefited from that. And there's been about 15 years of zinc finger clinical trials, so in gene editing technology. So regulators are, said another way, highly comfortable with working with companies in this field. And I won't go through everything in Europe, but it's very, very similar. They've got a slightly different process, but the overlap is more significant than the differences. More similar rather than the differences. Okay, so I'm going to tell a quick story. So in over Thanksgiving of 2018, so it was a Saturday, I got in my car, I left my family, my in-laws were over for a long weekend for Thanksgiving, and I drove off at about, probably about 10:30 at night, and I drove to the airport in Boston, where I waited to get on a 1:30 a.m. flight, technically Sunday morning, late Saturday night, really Sunday morning, to fly to Hong Kong for what I thought was going to be an incredibly boring and sleepy conference. There were initially going to be a whole bunch of biotech people there, and then the agenda got a little bit tripped up, and a bunch of panelists suddenly, weren't invited, frankly. And so I said, look, it's over Thanksgiving. It's not necessarily going to be great, but I'll go. So I fly over to Hong Kong. I leave at 1:30 in the morning on a Sunday. I land at, it was early Monday morning, Hong Kong time. I go get lunch. I'm hanging out, having lunch, half asleep. All I want to do is eat some food and then go take a nap, frankly. And then I was going to meet up with some colleagues at night. And I see on my iPad that there were the world's first genetically engineered twins that took place. And it was really, completely surreal. And this was a prospect I and many others had known technically could happen. But you think, hopefully no one's going to do something that stupid, frankly. and misuse the technology. And yet this fellow, Dr. Huh, did exactly that. And this was a Monday. By the time he came out on stage, it was a Wednesday, so a couple days later. It really took over the entire conference. I've never seen anything quite like it. And there were probably, 200, 250 cameras taking pictures of him, and the crush of media was overwhelming, frankly. And then, by that Wednesday, when he explained what he did, it was sort of even sadder and more tragic, because you realize he didn't really do informed consent around patients, really tell the parents what was really happening and the real risks, and he cut a lot of corners along the way. So really a sad, tragic, unfortunate series of events around what otherwise in somatic cells is generally considered to be a pretty promising technology. But it dawned on me, it's probably worth just taking a few minutes to talk about, if you think about this topic today, is do you want to be genetically engineered, and how is all of this sort of germline editing for clinical application, right, to actually do the editing and then have a child, how is it treated in the US, Europe, and globally? And so I've got a few slides on that. Bottom line, it's prohibited in the United States. Really, the FDA has really asserted for many years that any kind of alterations to a human embryo, you have to go through them. They rightly said, you just can't do this in some clinic. You got to come through us, and we're going to slow everything down. And so they actually require that you put together all the paperwork and do all the work to outline what is it you're trying to actually do and why, and like, does it make any sense? And they make you go through what would typically be like a clinical trial process. Well, in 2015, a bunch of people saw early experimentation that was going on for research purposes on embryos around using CRISPR gene editing, just to do research, not to deliver a child. And they moved pretty quickly and put together some language that by December of 2015, President Obama signed into law, and it expressly bars the FDA from considering any application in which a human embryo is intentionally created or modified to include a heritable genetic modification. So it essentially cuts off any legal path to doing what Dr. Huh did here in the United States. Interestingly, 7 months after Dr. Huh unveiled all of this, the House Appropriations Subcommittee looked like it might pull that language to prohibit gene editing and germline editing. And after a little bit of media attention and kind of a splash, they did an about face and restored the initial language from 2015, but not without a little bit of drama along the way. Europe, similar, prohibited. Interestingly, in Europe, they did this through a series of EU initiatives. The 2000 EU Charter on Fundamental Rights, Article 3, prohibits eugenic practices, and in particular those aiming at the selection of persons. And then really the kind of grounding treaty is what's commonly known as the Oviedo Convention, the 1997 Convention on Human Rights and Biomedicine, in which 29 out of the 47 European states approved it, and it states that requires that any therapy modifying the human genome may only be undertaken for preventative, diagnostic, or therapeutic purposes, and only if its aim is not to introduce any modification in the genome of any descendants. 18 of the European countries did not sign the Oviedo Accords, largely because they wanted to do more work on basic research, but by hook or by crook, they found ways to essentially preclude any kind of real germline editing for clinical purposes. And then an interesting document that someone told me about recently, a website I should say, recently is the Genetic Literacy Project has a global gene editing tracker. You can go in and kind of click on different regions around the world and take a look at how do they actually treat this. You see in the US and in Europe, that's prohibited. The language on the previous slide I largely borrowed and footnoted from the Genetic Literacy Project folks. But it's interesting, you can go in and see, there's not much regulation in Central America and Southeast Asia and parts of Africa. It's pretty light. And I think that's a little backdrop for some of our friends at the World Health Organization. So if you think about it, this issue, some people think, geez, this guy did this unfortunate thing in 2018, and hopefully it's kind of done and behind us. We don't have to worry about it anymore. Some of us thought maybe that was the case, but we weren't so convinced of it. And then a Russian scientist came along, I think it was in the summer of 2019, and said, I'm going to do the same experiment. I'm going to do it better scientifically. I'm going to go right through the regulatory authorities here in my native country of Russia. And I don't think they're going to stop me. And that caused a big sensation. And in parallel, the World Health Organization was putting together a global commission led by former FDA Commissioner Peggy Hamburg and by former South African Supreme Court Justice Edwin Cameron to look at, hey, we should probably have some kind of global governance on all this stuff. They've got a report due out in the first quarter of next year. It's unclear exactly what it'll cover, but they are looking at both somatic cell editing and germline editing. And then along the way, a lot of prominent academics have called for what Kevin referenced earlier, which is maybe we need some kind of a temporary global moratorium. Take 5 years to let everybody breathe, and let's just put a stop order in to the extent we can on any of this clinical germline editing. Eric Lander, the prominent head of the Broad Institute, organized with a bunch of colleagues internationally a letter from academics calling for a moratorium and got it published in a prominent journal. I'm very involved with the American Society of Gene and Cell Therapy. We did a letter with over 60 colleagues from a number of countries, many prominent academics and leading biotechnology researchers, to Secretary of Health and Human Services, Alex Azar, saying the same thing. There should be a global moratorium. And a lot of this convening, really, as Kevin mentioned, hasn't taken place for the last few years. There has not been a lot of great global forums to bring in and listen to the patient perspective, the bioethical perspective, the religious perspective, the company perspective, the physician perspective. And so more convening is clearly needed. And then, interestingly, the WHO Director General, when all of this was sort of playing on with this Russian scientist I mentioned, actually issued a pretty strong statement calling on all global regulators to not allow any gene editing to go forward for germline editing for clinical application. The WHO guys don't like to think of it as a moratorium. They don't like that term, but in effect, it is serving as almost a global moratorium for the moment, at least as called by the WHO. The topic today is really, do you want to be genetically engineered? And so I guess one of my things is, it's in reality almost, if you wanted to be, you almost couldn't do it legally in much of the country, the world. But what about the future? And I think it's a big question mark. Near term, there's this WHO work that's going on. No one really knows what's going to happen in Russia down the road. What's the future of the Aderholt Amendment that I mentioned? What will happen next year if there's a new Congress and a new administration, perhaps, and it's sort of anyone's guess what could happen there. And longer term, I think questions to kind of topics to grapple with include, what happens when there suddenly appears to be a relatively safe and effective, very specific application to a rare disorder, maybe like a Huntington's disease? Will that create demand out of the patient community, the academic community, to try germline editing for clinical application? I think that's a place to watch. There's talk, Peggy Hamburg has the term ethics dumping, which I hadn't heard before, but which is really to go in, should we really be worried about some havens being set up in some lightly regulated countries, sort of like we see with stem cell clinics? People just go in and you end up with medical tourism for the affluent and others. I think that is a concern. And then, and Kevin referenced this as well, I think there's going to be a day when we look back, and maybe it's in 10 years or 20 years, and we say, geez, wasn't it nice? We had time. The global community condemned what this Dr. Ha did, and this CRISPR technology will look quaint by comparison, because the technology will continue to evolve. And someday it'll be a lot easier to do some of this genetic engineering. And I do think now is the time when we should be putting some of this global governance in place. So I've got my personal opinions up here. The gene editing field is flourishing. It's a great thing. It really is a great thing for patients. There's a lot of innovation. Clinical trials are enrolling. The science is advancing. There's new technologies being pioneered, as I referenced. Companies are doing really well. They're raising money and they're fueling more research along the way. That's a positive. There is currently a robust regulatory framework for somatic cell editing in place, which is great. there can be more done in the developed world, and the WHO may help with that. And on the thorny germline issue, I really think the science isn't ready. You hear that from the prominent scientists. There's going to be a big debate, I think, about can you really do ethical clinical trials with germline editing? So I would watch that space. I know of no companies that are doing any work in germline editing. I think that's always important to say. And no country has expressly approved germline editing. Some guardrails are going to be needed. I just don't think it should be left country to country. It's too easy for some country to say, I'm going to allow it to happen. And I think that would be a tragedy. I think a global moratorium would be helpful. And I think, as I mentioned, other technologies will develop down the road. With that, I am happy and delighted to take any and all questions.
Okay, very good. Thank you, Tim. I have a question from a high school student. What do you think the bad effects of allowing us to have an immunity to cancer would be? With the HIV experiment, there were some side effects, and as a result, the girls didn't have a high immunity to other diseases. If someone had an immunity to cancer, wouldn't they be more open to other bad and weird diseases?
It's a good question. I think Kevin alluded to that. I think we just don't know. I think the knock-on effect of a lot of these things is just a giant question mark, because you'd think immunity to cancer. Kevin, I'll mention has this Laron syndrome. I think it is the story that he's taught me. I'll let him reference it, but it's one of those things where you say, hey, geez, here's a population of people that are, have a lower chance of diabetes and a lower chance of cancer, but would you want to be just like them? And people go, the more I hear, I'm not so sure. And it makes you think, well, what's the real disease? What does health look like? What is, how do we really think about this stuff? It isn't such a straight line. I referenced sickle cell disease earlier. I mean, there's and I'm going to get this probably a bit wrong, and the high school student can probably correct my science because he's closer to real science than I've been for some time, despite the fact that I've worked for biotech companies for a while. But sickle cell disorder, it's believed, developed as a way to combat malaria. It's sort of nature's way of allowing patients that had sickle cell disease didn't get malaria, and so there are pros and cons to all this stuff, and I think we just don't know. You tweak one thing, who knows what else could pop up. Kevin, you want to get a piece of that?
Sure. I mean, that's great. Hey, Tim, you're doing wonderfully well. You learned your science. That's fabulous. Just a couple of things. I mean, it's not just sickle cell. I think most people are familiar with the fact that if you carry one mutated sickle cell gene, you don't get the full sickle cell disease. You have what they call sickle cell trait, but you also have some additional resistance to malaria. Now, the interesting thing is, think of other diseases that that are the result of a particular mutation in a group of people that don't seem to make sense, because why would they be prevalent in that group of people if there's no advantage? And another one is cystic fibrosis. And so cystic fibrosis among Northern Europeans runs around 1 in 30, whereas cystic fibrosis in Asians, say in China, would be like 1 in 100,000. So why the difference? Well, there was this thing in Europe called the Black Plague. And it turns out that the mutation that causes cystic fibrosis, well, there's many, but that particular gene, if you have one mutated gene and one healthy gene, you have additional resistance to the bug that causes the Black Plague, Yersinia pestis. You also have additional resistance to tuberculosis, diphtheria, and other diseases. But if you have two of those bad genes, you have cystic fibrosis. That's how our genetics works. I mean, it's this intricate balance. And the group, if anybody is interested, you can Google this while you're listening. It's Laron, Laron. And Laron syndrome is a very rare, it's a group, there's a village down in Ecuador where some of these people have congregated, where they grew up, and they don't get cancer, ever. But if you ask people, do you want to be genetically engineered never to get cancer? Of course, you'll never grow more than 4.5 feet tall. Many people will say, well, it's not worth it. Not because you're sick in a sense, but in our society, if you're 4.5 feet tall, think of how you're treated. So not only do we have the genetic complexities here, but we even have the cultural complexities. Yeah, great point, Tim.
Great. Okay, we have another question from a high school student. She asks, when we are speaking about the future, how far off do you believe it will be until we could see gene editing? Also, with trial runs, would this be done on animals or on humans?
Yeah, so was the question around gene editing or germline editing? How soon will we see gene editing?
Gene editing.
Okay, well, let me take a poke at both. So gene editing, as I mentioned, the clinical trials are going on right now. So, how soon could it be that we would get things approved through the FDA or the EMA? I would say certainly in the next 3 years at the most aggressive, probably more likely 5 to 7. By the time you actually go through probably you need 2 sets of clinical trials. It's possible with some of these disorders you could do one. You could sort of do a phase 1, phase 2, and then add some patients and make it a really condensed trial if it's small enough population, and go to the FDA file and get something approved. So that's the 3 years, perhaps. And then I think 5 to 7 is more likely, certainly in 10 years, but I would say sooner. So that's what would be, maybe I'll just hold it at that. That's my best guess on a timeline.
Okay. Another question, would mitochondrial replacement therapy be considered germline therapy?
Wow, these are great questions.
Very good question.
Sorry, would it be considered germline therapy? Was
germline therapy.
Yeah. It is, I'll start and then I'll have Kevin mop up my mess. This comes up from time to time. So mitochondrial transfer is, let me break it into parts. It is not considered gene editing. It is more, I believe, like gene therapy. It's sometimes called 3-parent babies. It is precluded by the same provision, the Aderholt Amendment, that I referenced earlier in the United States. So right now, there's no legal path forward to do it. I would say some scientists are very encouraged by it, enthusiastic about it. I have no doubt there are some in the mitochondrial community that are enthusiastic about it. I believe there are clinical trials going on in the UK and some other countries. There was I think a case of a U.S. physician that went into Mexico and did the actual procedure. I think, frankly, the technology is still pretty early, emergent, unclear, and it's a heritable change. I would think it's considered germline, a germline alteration of some form, primarily using gene therapy. I know it's heritable, and I know it's not gene editing. Whether it's technically considered germline, I'm not sure. Kevin, how am I doing?
We're going to give you an A for all the hard work that you've been doing on your science. This is good. It's a good distinction, in fact. So what's going on is you're not fixing the genetic mistake. You're replacing the bad mitochondria. So for people who are not as familiar with cellular biology, the cell, like cities, has to have a power source. You have to have some kind of place that generates the power. And in cells, that's the mitochondria. And it's the little power plant of the cell. And if the genetics that's in the mitochondria is separate than the genetics that's in the nucleus of the cell. But if you have mutations in that genetics, that can cause the mitochondria to not function well. Now you have lots of mitochondria in every cell. Problem is, some of these mutations in the mitochondria make it easier for those mitochondria to make more mitochondria than the ones that are normal. That's when you run into trouble. So the idea here is replace the bad mitochondria in the cell with good mitochondria. Well, it's a great idea. How do you do that? Well, you don't. Basically, as Tim said, the technology's not there yet. What they're attempting to do is say, all right, we'll take a very early embryo, say 1 cell. And now, instead of that cell having the bad mitochondria that came from mom, we'll take the genetic material out of that cell and put it in a different cell, a different egg that's had its genetic material removed and yet has the healthy mitochondria, and put it in there. And then have that organism grow up. So, answer, is it germline? Absolutely, because it's in the first cell of the body, so it goes into every cell of the body. Does it work? You know, there again, that's the argument back and forth. Obviously, one answer to that argument is, well, the only way we're going to know is do the experiments and try it. Of course, as Tim pointed out, this is with human embryos. So that's where the other issue comes in. Now, can you do these in animal experiments? They're doing animal experiments, primate experiments, all that with that. Again, it is very early on. Now, the interesting question here is some people are now looking at, well, wait a minute, we've got CRISPR, or we've got these other newer technologies like Tim mentioned, base editing and primer editing. So the idea is, could we go in and change the mutations in the mitochondria? Now, there's a really interesting question, because then that actually could benefit the person now who has the disease. So that is very much in its infancy.
Yeah, and I would also, Sheila, thanks, Kevin. I would also add, this topic does get a lot of attention. I think at some level, it's a combination of you have an organized, focused, understandably, patient community that's really anxious to get options for patients, which who can blame them, right? There was I think it was a National Institute of Medicine report or something that came out some years ago that said, geez, this could be promising. And then the Zaderhold Amendment came in and kind of precluded it. What doesn't get discussed is there is actually more companies springing up, doing more work in cell therapy and other things specifically to help mitochondrial disorders. And I know this because a friend of mine became a chairman of the board of one of these companies and said, it's an Israeli company. He's like, this is incredible, the work they're doing. Incredible. And we're really hopeful that we can get clinical trials up and running. And in fact, they may be dosing patients now. So I don't think it gets portrayed as sometimes an either or choice. Either you're for mitochondrial transfer or you must not care about either advancing technology or helping patients. That's a false choice. In my view, there is other real important work that's being done, and Kevin alludes to maybe some CRISPR work being done, but also I know cell therapy work being done. So.
Okay, very good. Another question. Has any research been done on COVID-19? Are certain populations more susceptible to this virus related to gene mutations?
I think there's been some academic work. I don't believe there's been a big company push to do work on COVID. I think one of the challenges is with still a fairly emergent technology, it's hard to turn on a dime and say, let's go quickly and chase after, as tragic as COVID-19 has been, a disease, a virus that could be up and down and gone for drug development timelines, a pretty compressed amount of time. And the work that's being done on vaccines and antibodies and using mRNA and everything else, it just seems like strikes me as it's way ahead of where CRISPR would be. So they could turn quickly, apply it in a very targeted manner, have an impact, get real clinical trials up and running, and get up and down on it efficiently. And I just don't think, in my estimation, is that CRISPR you wouldn't want to move that quickly. You certainly wouldn't want to use it I wouldn't think for a vaccine right now, or necessarily even a great therapeutic. So I have not heard of a lot of work being done toward COVID.
Okay. Have there been consistent negative anomalies in treating sickle cell anemia that have been generally accepted by those with sickle cell anemia in order to extend their life and improve their well-being? How much longer do those live once they're treated?
Okay, anomalies. I'm not familiar with that. I guess I would say couple of things on the sickle cell population. I think it's general. I'm going to grossly generalize, right? It's a tough area. There has not been a lot of innovation. There's been something like 2 drugs approved over the last, I would say, 30 or 40 years for the sickle cell population. It has come up as a good example of something where some people have said, hey, look, this doesn't feel like it's exactly fair. The biology is somewhat straightforward. How come there haven't been more innovations, frankly, in this space? And I think now what you're seeing is, very compressed amount of time, like within 5-7 years, you now have, 7 or 8 clinical trials going on between gene therapy and gene editing, and then some other traditional modalities to try to help sickle cell patients. You see this a lot. You see these bursts that sometimes happen once the biology is better understood, or people think they can apply the biology, the technology, to the underlying biology. Like we saw this in hepatitis C, right? Very low innovation for many years. You might get a therapy that would help a little bit, but not that great. And then within like 5 years, you had a flowering of innovation, and companies that were working on it, suddenly they got, it was almost like the tech market. A better iPhone came out, and they were gone, and really rapid. And now, within a very small amount of time, like if not now, then within the next couple of years, we're not talking about hepatitis C anymore, because it's an all oral regimen that's that can wipe it out, and it's great. That would be great for sickle cell. I think there are complexities. It's, as I said, in the United States, it's almost all, 90% of the population in the United States is probably African American. Probably by most estimates, 75-80% of the population is in the Medicaid programs. And at the end of the day, a lot of times these therapies, gene therapies or gene editing technologies, when they eventually get approved, will be very expensive. They take 10 years to develop, oftentimes, all in. And so putting all those factors together, I think it's going to be a trick. And I think it's not necessarily going to be easy to recruit patients to clinical trials, nor when there's actually a therapeutic option. A lot of times people are going to be like, hey, this, it's sort of like you hear this with the vaccines for COVID. But I'm glad they're doing a vaccine. I'm not sure I want to be the first person to get it, right? So I think there's some skepticism that I've heard about in the community, with the African American population, there aren't that many gene therapies that have been approved, and we people talk about Tuskegee. It wasn't that long ago when there were experimentations going on the African American population, and we're not happy about it. And so you want to take a new modality, and whether it's gene editing or gene therapy, and apply it to, we like innovation, but let's just make sure let's measure twice and cut once, which I can understand.
Okay, thank you. Another question. The Nobel Prize aside, there has been a big intellectual property battle with some of the leading academic groups for a few years related to CRISPR gene editing. Can you give us an update on this, and how do you see it playing out, and what impact does it have on patients?
Yeah, good topic. So, there's less noise today about the intellectual property battles than there was 4 or 5 years ago. When I first joined Editas in January 2016, it was like all you could hear about was intellectual property. And the short and simple version is there's a number of important academic institutions and researchers that did pioneering, really groundbreaking work around CRISPR in sort of 2010 to 2013 timeframe. Emmanuel Charpentier and Jennifer Doudna did terrific work. I mentioned Feng Zhang did great work at the Broad Institute. And out of all that, there became a dispute because the leading kind of patent in the area went to the Broad Institute. And the folks at University of California, Berkeley weren't super happy with that. And so, to put it mildly, and then there are other important universities in Lithuania and and I mentioned Mass General and Harvard and MIT, lots of intellectual property was amassed in a pretty compressed amount of time. A lot of people said, this is all seriously important work. Let's file for intellectual property rights. All that intellectual property, much of that intellectual property got licensed out to companies. That's the backbone that helped build up the companies. And oh, by the way, that's just in the United States. Then you go to Europe, you go around the world, Japan. There's even more layers of intellectual property that gets filed and stuff like that. What you're seeing now is that's all kind of shaking out. There's been many legal battles that have taken place to date, and there will be many legal battles that will take place into the future. I think the bottom line for patients is it's all going to get hashed out, in my view. Typically what you see when you go back, you skip back for the last 40 to 50 years of innovation around biotechnology, is you end up with a lot of cross-licensing, and groups make their intellectual property available, and if a product gets approved by the FDA, you pay some licensing fees and things like that. But both the pioneering work was real and important. The work being done in clinical trials to help patients is very real and important. And as I mentioned earlier, there is just a ton of additional innovation that's going on, which is great. So you see a flowering of lots of important stuff, despite the fact that there's this sort of background noise around intellectual property disputes.
Yeah. Okay. Another question. We have a few more minutes. Is safety and off-target effects the main roadblock? What other considerations should go into the conversation of permissibility?
Yeah, that sounds like it's directed towards germline editing. Let me just do a quick touch on somatic cell editing. So safety and off targets and on targets, and how do you hit exactly what you want to hit, and how do you know, has been one of the kind of major early riddles in the somatic cell editing. And a guy named Keith Jung at Mass General is one of the kind of global pioneers at literally going in and figuring out, how do you measure? How do you know that you did what you wanted to do at a cellular level? And make sure that when you say you want to take out this gene, you're taking out this gene and this gene only, and it's not skipping into other areas, right? Commonly called off targets. And so that work has been very, very robust and advanced dramatically, I would say, in the last 5 years, to the point where the FDA is pretty confident that the companies collectively and the leading academic institutions collectively have a reasonable handle on it. But we'll see. Time will tell. The more patients you dose, again, it's drug discovery and development. So we'll see. I think a ton of work is going to need to be done before you could ever think of really safely dosing or undertaking germline editing. If you could do it ethically, and if you just locked in on, do we think it could be done safely? There's so much that's just not known, frankly, about the early days of development of an embryo, and what's the impact of this technology. So I keep referencing, he's a friend and colleague of mine and Kevin's, Keith Jung. You know, he's really the leader in how do you measure on targets and off targets. He's extremely concerned about the long-term implications of germline editing because of all the stuff he does understand and the stuff that he doesn't understand. And so I think it's a tall scientific order. It would not surprise me if we were having this similar discussion in 10 years. So yeah, okay. It's one of many major hurdles. I mean, Eventually the science, given enough time and enough money and enough brain power, a lot of this stuff can get unlocked, but this one's not going to be quick, in my view.
Okay. All right. Thank you very much, Tim. I'm going to turn it back over to Tom for the next.
Well,
thank you.
Thank you very much, Tim and Kevin, too. And now that our audience has been introduced to this field, they've seen some of its applications, you can see that many diverse possible directions lie ahead. Therefore, it's time to look at the ethical issues involved, and for that aspect, we have Richard Dorflinger. Now, Richard Dorflinger has an MA in Divinity from the University of Chicago. He has pursued doctoral studies in theology there and at the Catholic University of America. For 36 years, he researched and drafted resources on bioethical issues for the U.S. Conference of Catholic Bishops, and now writes a monthly column for the Catholic News Service. He is a fellow at the University of Notre Dame's De Nicola Center for Ethics and Culture and at the National Catholic Bioethics Center, and is a member of the Genomics Working Group at the Pontifical Academy for Life. He and his wife Leanne and their aging golden retriever Colby live in La Conner, Washington. His presentation is titled Human Gene Editing and Human Dignity. Richard.
Thank you very much, Tom. Let's see. Here we are. Thank you. Glad to be with you today. The reason we did the presentations in this order is that, as Tim Hunt said, we're talking about both hopes and fears about gene editing. And you've already heard a great deal about the hopes for correcting terrible genetic defects and diseases. It's my happy task to talk about the fears. And that's very suited to my dour personality. The secular ethicist who disagreed with me on the issue once called me the Cassandra of embryonic stem cell research. And I thought that was really appropriate because in the Greek myth, Cassandra asked the gods for the gift of foretelling the future. And she had ticked off some of the gods. And so her blessing became a curse. What they gave her was the ability to foretell the future. It would only be about horrible things, would always be absolutely accurate, and nobody would ever believe her. And I felt that the Catholic Church has been in the Cassandra position on a number of these things. There's an old friend of mine, Nigel Cameron, Scottish ethicist, who many years ago said to me, you know, for a long time we've been dealing with the issues of taking life, whether it's abortion, euthanasia, or destruction of human embryos. Now we're entering the issues of making life, reproductive technologies, in vitro fertilization, human cloning. But now we're going to be heading into the issues of gene editing and artificial chromosomes, and we'll be faking life. I don't know if that's really an accurate description, but my point here is that when you enter the field in which the fears are greatest, the concerns are greatest, and that is germline editing and moving from therapy to things that are clearly enhancement, all of those concerns about life and about procreation and about changing human nature all come into play at once. So let me start up here my PowerPoint, which is much more boring than those of others. It's all just straight text, and we'll proceed. A lot of these concerns and this group of concerns about germline gene editing have been treated by a lot of organizations and individuals under the heading of human dignity. The President's Council on Bioethics years ago did an entire book of essays about human dignity and bioethics, trying to figure out what is that and is it a valid concept. There are two international organizations, the most international and multicultural organizations, in a sense, in the world, that have talked about this in terms of human dignity. The first of these is the United Nations. Now, why am I not being able to advance my own slides? I'm sorry, just a second. So what's all this about dignity? We look to the United Nations Universal Declaration on the Human Genome and Human Rights. This was prepared by UNESCO in 1997 and endorsed by the General Assembly of the UN in 1998. And Article 2 begins, everyone has a right to respect for their dignity and for their rights, regardless of their genetic characteristics. That dignity makes it imperative not to reduce individuals to their genetic characteristics and to respect their uniqueness and diversity. And Father Kevin talked a bit about that diversity we don't want to lose. The concept of human dignity as grounding human rights goes all the way back to the UN's first Universal Declaration of Human Rights back in 1948. whereas recognition of the inherent dignity and of the equal and inalienable rights of all members of the human family is the foundation of freedom, justice, and peace in the world. She had all these diverse nations of the world with many different cultures, many different legal systems, all agreeing on the list of what the basic human rights are, which was an amazing achievement. And they all said, all of these come from our innate human dignity. The UNESCO Declaration on the Genome goes on to say that no research or research applications concerning the human genome should prevail over respect for the human rights, fundamental freedoms, and human dignity of individuals, or, where applicable, of groups of people. So this triad, human rights, fundamental freedoms, human dignity, occurs throughout these UN documents as this triad. They're distinct from each other, but they all relate to each other. And the declaration said the International Bioethics Committee of UNESCO should be giving advice on follow-up, in particular on identifying practices that could be contrary to human dignity, such as germline interventions. Note it says could be contrary, but that was the area where this concern was most urgent. Then in 2005, you have the UN's Declaration on Human Cloning. It's a declaration, it's not a legally binding covenant or treaty, but it was a declaration that was approved by 84 nations, voted against by 34, with 37 abstentions. And I'll go into the reason for that in a moment. Member states are called upon to prohibit all forms of human cloning inasmuch as they are incompatible with human dignity and the protection of human life. Member states further called upon to adopt the measures necessary to prohibit the application of genetic engineering techniques that may be contrary to human dignity. That's again repeating the 1997-1998 Declaration on the Genome. The reason for the large number of abstentions is that some nations wanted to leave open the possibility of using human cloning for embryo research to, for example, produce embryos that would be a clone of an existing patient and then destroying that embryo to get its genetically matched stem cells for treating that patient, and so on. Some call that therapeutic cloning, though no therapy has ever resulted from it. And they were willing to ban reproductive cloning, where you take the embryo and allow that to survive to be born alive. The majority who voted for the declaration pointed out two things. One is, we don't like the idea of creating human embryos in the laboratory solely in order to destroy them. In fact, way back in the debate on embryo research that happened in the US in the 1990s, you even had the editorial board of the Washington Post, certainly no organ of the pro-life movement, saying creating embryos solely for research that will destroy them is unconscionable. But the second point that the majority nations raised was, if you do this for embryos that are then going to be discarded, all you're doing is refining and perfecting the technique that will then increase the pressure to say, now we are ready, now we know the risk-benefit calculus here, and now we are ready to do this and make cloned babies. And so they said, if all you do is right now ban reproduction to live birth, you're not doing a ban, you're doing a speed bump. You're just giving the researchers the go-ahead to get it right in their view, in practical terms, and then do everything that you say you're against. Exactly that same issue is occurring now with germline gene editing. A number of international organizations and the American Society for Human Genetics, for example, put out a statement in 2017 that said exactly this. Let's do germline gene editing on embryos. We will discard them, we promise, but right now we will not allow them to survive to birth. But that ends up becoming just step two. You're doing a speed bump, but when you think you've got it right, it is almost inevitable that people will do this for live babies as well. One of the science journalists who was covering the Society for Human Genetics statement, did the article with the headline, "Editing Human Embryos is Okay, but don't turn them into people yet." So then we have a debate about when are you people? But that's a very old debate. Now, here's the second international institution. Father Kevin already referred to this. The Catholic Church is perhaps the most international and multicultural organization in the world because it has adherents and it has some infrastructure in virtually every country in the world. It also was very involved, some Catholic philosophers were very involved in the preparation of the Universal Declaration on Human Rights. And the reason I go to the Catholic documents here is because the UN has always refused to go any deeper into what does it mean by human dignity. Jacques Maritain, one of the philosophers involved, he told a story once about somebody at one of the UNESCO meetings saying to one of the philosophers who was involved, "This is incredible that with all your different nations and ideologies, you actually managed to agree on what the human rights are." And the person replied, "That's right, we agreed on what they are on condition that no one ask us why." But Catholic Church is among those that has tried to say why there is human dignity. And has done so in a way that, because of the natural law tradition in the Catholic Church, is also open to being restated in more general philosophical terms that do not require religious belief. And for that reason, I want to talk a little about the Catholic documents, which have been talking about gene editing in humans at least since the early 1980s. And here's the Vatican instruction on respect for human life and its origin and on the dignity of procreation, 1987, mainly about reproductive technologies, but also said certain attempts to influence chromosomic or genetic inheritance are not therapeutic, but are aimed at producing human beings selected according to sex or other predetermined qualities. These manipulations are contrary to the personal dignity of the human being and his or her integrity and identity. Every person must be respected for himself. In this consists the dignity and right of every human being from his or her beginning. The idea is that dignity is innate in each human being. It is our abilities are not equal, but our dignity is equal because we are all equally members of the human family. Pope John Paul II, even earlier, talking to the World Medical Association in 1983, asked about whether genetic manipulation can be reconciled with the human being's innate dignity and untouchable autonomy. And he spoke in favor of a strictly therapeutic intervention whose explicit objective is the healing of various maladies, such as those stemming from deficiencies of chromosomes. In principle, that's considered desirable. The ethical issues here are of the same kind that would be found in any experimental treatment. They're not qualitatively different. Whether you are treating the human being and who is your research subject as just a means to the health of others, or whether you might be able to benefit that person, to get that person's informed consent, and to make sure that you're actually serving the well-being of this person. But then on non-therapeutic interventions, he said genetic manipulation becomes arbitrary and unjust when it reduces life to an object, when it forgets that it is dealing with a human subject, capable of intelligence and freedom, worthy of respect, whatever may be their limitations, but when it treats the person in terms of criteria not founded on the integral reality of the human person at the risk of infringing upon his dignity. We have actually somewhat at war. We have a couple of different meanings of what human dignity is. One meaning of human dignity is the dignity of achievement, of excellence, of being able to pursue and achieve your aspirations. That's the dignity of autonomy. Autonomy has been a very powerful theme in bioethics since the founding of bioethics in the 20th century. The ability to define yourself and remake yourself. Steven Pinker, a social psychologist at Harvard, is one of the authors who has criticized the whole idea of dignity. He has an article called The Stupidity of Dignity. And what he means by that is the word dignity doesn't add anything to the simple concept of autonomy. If you're serving the individual's autonomy, then you are serving that human person, and that's all there is to it. The rest of this is just superstition and eyewash. And that idea of dignity ties in very much with what has been called the dominant worldview of our time in the modern democracies, expressive individualism. I define myself by my desires, and I remake myself in that way. Sociologist Robert Bellah has referred to this worldview in his Habits of the Heart. Philosopher Charles Taylor has as well. There's a new book out on bioethics, by the way, by Carter Sneed of Notre Dame. That is, the whole book is a critique of expressive individualism as a criterion for bioethics. But it means transcending one's given characteristics, potentially in transhuman or post-human enhancements, potentially transcending even one's nature. If you think I'm overstating this, here's one comment by ethicist John Harris. He endorses in his book on clones, genes, and immortality the creation of a superior new breed. It would actually be a new species that would not be capable of reproducing with Homo sapiens. That's one of the evolutionary tests for whether you're a different species. You can't reproduce with the other one. Yale microbiologist Lee Silver, in his book Remaking Eden, he takes it a step further. He talks about this new species ascending to the point where, and this is after, I suppose, they put the rest of us in zoos as the animal species they've transcended, but I'm not sure of that. But these people now look to the heavens to see the face of God and find out that they're only looking in a mirror. So this is self-divinization now, the remaking Eden. It's interesting that all of the very secular scientists who write books about this seem to be talking about the Garden of Eden, immortality, and becoming gods, even though they would be the first to tell you they don't believe in God. They think the job is empty, and so it is our task to fill that in. Now, here's the problem with autonomy as dignity. First of all, it's not what the United Nations meant, because they were treating dignity as something distinct from and perhaps grounding autonomy as well as rights. So they mean something different and more basic by that. The paradox is, and this is something C.S. Lewis pointed out in the 1940s in his The Abolition of Man, when man turns his ability to master nature against human nature, that becomes the mastery of some people over other people. It's my autonomy controlling the evolution of you. And of course, if you are editing human embryos to control what their capabilities are, it's useless to ask the embryo, do you want to be genetically engineered? Because someone else has already decided that for you and will now have expectations of you based on what they designed into you. And so mankind becomes not only the controller of nature, but the controlled, the person who is the object of someone else's freedom. And it easily becomes freedom over and against others, the power of the strong over the weak. I call this hard coercion. Gene editing is among other things, could be a tool for very totalitarian governments to control their population. Jennifer Doudna, who is a very brilliant and very thoughtful scientist, she once talked about having developed this CRISPR gene editing technique. She said she's had a nightmare in which Adolf Hitler comes to her and says, "So, how does this CRISPR thing work?" And that's the extreme case of hard coercion. I'm actually more interested in soft coercion, by which I mean the subtle power of accumulated free choices and societal expectations to put pressure on people based on those expectations. For example, you have a parent who has engineered a child to be a great concert pianist or a genius or the greatest athlete who was ever born. That child was created from the outset to be a carrier of those preferred traits. What happens if the child, as he or she grows up, has ideas of his or her own and wants to play the banjo or is not that interested in science, but wants to be a religious brother or a sister. Are we then tempted to have conditional love? You saying, this is not what I had in mind, this is not the reason you were even created, and apply those pressures. Dr. Robert Edwards, who is the co-creator, if you will, of human in vitro fertilization, said 20 years ago, soon it will be a sin of parents to have a child that carries the heavy burden of genetic disease. So even with the idea of treating disease, you have the pressures of what if somebody wants to reproduce in such a way that their child is not engineered, but is to be a surprise, as all of us now are to our own parents currently. Iceland had an announcement. The public health authority in Iceland made the boast some years ago that in just a few more years, there would not be a single child born alive with Down syndrome. The way they put it was, we will have eliminated Down syndrome, and what they mean is that by prenatal diagnosis and by selective abortion, there will be no live-born children that carry Down syndrome. What if somebody just goes ahead and refuses the diagnosis or the abortion and has such a child? Where's the social support for that child? Where is going to be the enhanced stigma when people look at this child and say, don't you know you had the right and to some extent the obligation in the eyes of the rest of us to take care of this problem? This is the soft coercion of expectations. We already have an issue of autonomy becoming something of its opposite in the field of women's athletics. Title IX of the Education Amendments of 1972 required educational institutions to give equitable support for women's athletics as well as men's athletics. And now we have a new era of transgenderism in which, and this is very much a part of expressive individualism, people are to be treated as having the gender that they decide they wish to be identified as. You now have the phenomenon, which is a great concern to feminists, to mainstream feminists, that men who identify as women are winning a lot of the women's sports tournaments because of the fact that their genes and the testosterone that those genes gave rise to have been bathing their cells with factors that enable them to have greater upper body strength and greater speed and so on. And so in the end, it may be that no woman is going to be free to compete with her peers on a fair basis in a whole variety of women's sports that rely on that greater musculature and that upper body strength and so on. My favorite example of soft coercion in popular culture is the movie Gattaca. And the interesting thing about Gattaca is that it is illegal in the future society of Gattaca to discriminate against people because of their genome. There are some people who reproduce in the old-fashioned way. They are called the invalids, which is lovely because it's spelled the same way as invalid, which means you're kind of sick compared to other people. And so genoism, genetic discrimination, is illegal, but as the narrator says, nobody pays the law much serious attention. There are always ways to find out whether someone was genetically enhanced or not. And those people simply find out they can't get the really exciting and challenging jobs. And the story of Gattaca is the story of someone who is not genetically enhanced, who is committed to fulfilling his dreams, even though only the genetically enhanced are supposed to be doing that. During the question period, I could talk literally for hours about Gattaca, but let me move on. Here's a richer meaning of dignity that I think the Catholic Church is proposing, and I think the UN also had in mind. It is not reducible to particular rights or freedoms, but grounds them. It is equal in all human beings, and that's why it can ground equal rights, equal respect for everyone. It is not about equal abilities. Is it about the fact that equally we are all heirs to this special thing that is human nature? The dignity is innate because of the unique composite nature of human beings. Theologically, I would say we are embodied souls or ensouled bodies. We have both the material and the spiritual. We are a microcosm of the whole range of possible beings in creation. We have the given and the transcendent. We are neither beast nor God, which is the title of a wonderful short book by Lutheran ethicist Gilbert Meilander about human dignity. Gil Meilander refers to this as the strange in-betweenness of our human condition. That we are the only being that is both animal and rational. Mark Twain once, maybe he was summing this up by saying, the human being is the only creature that can blush or needs to. Our bodies and souls don't always work that well together. The harmony between them is ideally complete, but we always have that tension between what we are given by the lottery, if you will, of creation, or I would say the giftedness of our creation, and our aspirations and hopes for fulfilling our potential. This is not a dignity that has to do with perfection. Because of those tensions, it's a call to recognize one's imperfections, and it is a call to join with others to address those imperfections through our bonds with those who complement us. Marriage and family would be a paradigm situation of that. A friend of mine recently said that by marrying his wife, he had married up, and I corrected him and said, we all of us men marry up. But the complementarity of the sexes is one aspect of the complementarity of all human beings who each have their strengths and weaknesses. And so our dignity is also a communal thing. It's a social thing. It is not a competition. It is a call to solidarity. And here's a couple of quotes that illustrate this in terms of the Catholic documents. Each human person in his absolutely unique singularity is constituted not only by his spirit, but his body as well. To respect the dignity of man amounts to safeguarding this identity of the man corpore et anima unis, one in soul and body. It's on the basis of this anthropological vision one should find the fundamental criteria for decision-making in the case of not strictly therapeutic interventions, for example, those aimed at the amelioration of the human biological condition. And he pointed to the ambiguity of the word genetic manipulation, because that could mean what he calls adventuresome endeavors aimed at promoting I know not what kind of Superman, and on the other hand, salutary interventions correcting anomalies such as hereditary illnesses. And he suggested the term genetic surgery for those latter things, the somatic, the therapeutic interventions, because medicine there is intervening not to modify nature, but to favor its development according to its own essence, that of the creation that intended by God. That's a phrase that is also quoted and reaffirmed by Pope Francis in his encyclical on the environment, Laudato Si. The English translation of this, by the way, is awful. It says, according to its own line, whatever that means, but the Latin and the Italian are very clearly according to its own essence. There is a great fear that in departing from the basics of human nature, we are losing our human dignity and disrupting the harmony we do have between the spiritual and the material. And here's a document from 2020, this year, Samaritanus Bonus, the Good Samaritan. It's not on gene editing, it's on euthanasia. But it makes an interesting observation that the need for medical care is born in the vulnerability of the human condition in its finitude and limitations. Each person's vulnerability is encoded in our nature as a unity of body and soul. We are materially and temporally finite, yet we have a longing for the infinite and a destiny that is eternal. Our vulnerability forms the basis for an ethics of care, especially in the medical field. So I'm seconding what Father Kevin said about technological progress needs to be corrected by asking, are we really heading for an ethics of care for all? Human dignity does not demand a quietism or an opposition in the face of gene therapy or other medical advances, but it is a check on unlimited redefining and refashioning of myself and others. It involves a sense of humility before the givenness. And to someone who believes in God, as I do, I would say before the gift, the unique gift of our humanity, which we do not invent but discover, and we discover it in our diversity and our strengths and weaknesses. Finally, I just want to end with this because the President's Council on Bioethics, which I already mentioned, had a book, a report called Beyond Therapy, which is about this whole field. Very interesting report. And they ended with essential sources of concern about unlimited gene editing. They did 5 of them. I'm just going to look at 3 very briefly. They're really questions. In wanting to become more than we are, and in sometimes acting as if we were already superhuman or divine, do we risk despising what we are and neglecting what we have? Do we lose that appreciation for the givenness, the giftedness of our nature and our world, and our ability to discern what is already good in us, what can be improved, and what is a kind of hubris, a kind of overweening pride to be resisted, playing God without anything like divine wisdom. Second one, in wanting to improve our bodies and our minds using new tools to enhance their performance, we risk making our bodies and minds little different from our tools, in the process compromising the distinctly human character of our agency and activity. We see this already, of course, in athletics. We were talking about blood doping. If athletics ends up being taken over by people who are simply genetically enhanced to be the strongest and have the greatest stamina and the greatest speed, will people even pay attention anymore to what sports are for? Because we are no longer looking at the great achievements that people have by disciplining themselves and exercising their abilities and fulfilling their potential, when that potential is simply built in, and all we can do is thank not their self-discipline and their activity, but their geneticist. Finally, in seeking brighter outlooks, reliable contentment, and dependable feelings of self-esteem in ways that bypass their usual natural sources, we risk flattening our souls, lowering our aspirations, and weakening our loves and attachments. If we have become the perfect person, do we need anybody else anymore? If we, like the people in Brave New World, we know exactly where we belong in society because we were engineered that way. And when we get dissatisfied with any of it, we use soma to make ourselves mellow out and feel happy artificially. What happens then even to the meaning of happiness when it is disjointed from the real sources of happiness? So, final thought. The question is, what does it mean to be human, to have human dignity? What is good about being human that we shouldn't tinker with? If we can't answer those questions, how do we know what a better human would be if we don't know what a good human is? And those questions go well beyond the realm of science. Scientists alone cannot answer them. They are directed to all of us. And as Father Kevin said, whether theologians, the people who are most in need in our society and in other societies, the marginalized, the philosophers, the sociologists, and the answers of all of us may well help determine the human future for all future generations. Thank you very much.
Okay, thank you, Richard. We've got quite a few interesting questions on this topic, and certainly bring them up. And we're going back once again to Sheila Roth at iTest in St. Louis for the compendium of questions.
Okay, thank you, Tom. Thank you, Richard. The first question is, looking at soft coercion and ableism, do you see that developing a more inclusive community is mutually exclusive with germline editing? Is it possible to use germline edits in a therapeutic way and avoid eugenic practices?
I think there is. In fact, Pope John Paul II in his 1983 address even talked about the possibility of doing a germline intervention, let's say to correct a one chromosome, a defect like one of the trisomies. The germline intervention that would then free that person and all of that person's descendants from that fear of having a terrible genetic defect that is incompatible with survival. But he also said, because the church also has a great concern about the depersonalizing of procreation through in vitro fertilization and about the great loss of human embryos that are endemic in that practice, he was saying, can we have scientists develop a way to do even that germline intervention with people who reproduce naturally? The people who reproduce naturally in Gattaca are, what are they called? Faith births. But in fact, one of the characters says to another one, you mean, to find out he's not genetically enhanced, she says, you're a God child? So I feel happy as a Catholic to be on the side of the God child. But so you have the question of how are you going to do it? And if you're going to do it and you really know for sure that this is not going to have some kind of terrible effects down the road for future generations, if it is really a strictly therapeutic intervention of the kind that we're talking about now for diseases and serious life-threatening defects, I think the Catholic Church would be saying that is valid if you can fulfill those criteria and if you can do this without harmful embryo experimentation, by treating this child when he or she is still in a very early stage in the womb, for example. I think we were saying the same thing about embryonic stem cell research for many years about why can't we be developing this technology in a way that doesn't have any of the moral problems? And people said, they brushed it off and said, no, we have no evidence that that's going to happen. Then in 2007, Shinya Yamanaka develops induced pluripotent stem cells that can reprogram ordinary adult cells into embryonic-like cells that are a perfect genetic match to the patient you're trying to treat. He wins the Nobel Prize, and even some of the originators of embryonic stem cell research in humans heave a sigh of relief and say, we're so glad we can pursue this now without the moral problem. So we'd want to look at how that can be done, and we think the church wants to be, I think, a promoter of scientific progress that provides a richer menu of alternatives to things that do pose an ethical problem.
Okay, thank you. Where does the idea of human dignity grounding human rights come from? Did the Church or the United Nations come up with it first?
Well, the idea of human dignity itself, we find that in, you can find it in Thomas Aquinas, but it's originally in a very theological context. I actually wrote down somewhere one of St. Thomas Aquinas' many references to the dignity of human nature. Of course, theologically, in the Catholic tradition, it's based on the idea that each one of us, in our own diverse ways, is made in the image and likeness of God, and that's where that special dignity of human nature comes from. And you find it, interestingly enough, most of all in Aquinas, in discussions of the incarnation, in the third part of the Summa Theologiae, where he talks about Christ giving the ultimate affirmation to the dignity of human nature by being willing to become a human being among human beings, that God himself was willing to do that. But if you want to look for human dignity as grounding human rights, you'll find it very, very frequently stated in the 19th century in the social encyclicals of Pope Leo XIII. In 1881, in his document on human liberty, and then in 1888, and then in 1893, in his much more well-known encyclical on the rights of workers, Rerum Novarum, where he talks about every employer having to recognize that every employee is not his bondservant or his slave, but as a person equal in human dignity to himself and to be treated the same way. So I think the church was there first, but they're also not totally independent, because some of the philosophers who ended up developing the Universal Declaration of Human Rights were themselves Catholic philosophers, and even some of the national leaders who worked on it had a Catholic background of their own.
Okay, very good answer. Thank you. Are there any notable distinctions between Catholic universities and hospitals from the secular institutions in either research or application around this area?
That's a very good question. I actually was on an advisory group that advised a Catholic university some years ago about the fact that for a great many applications in biology, the gold standard for culturing new preparations is immortalized cell lines based on fetal tissue from abortions. And this university was very concerned about this. I don't want to talk about who it was, because the document they worked up has not been made public, but they changed their practices in accord with our advice. And the idea was, without having to discontinue or block everybody's research that's already ongoing here and now, because your research in a lot of fields won't even be accepted by a peer-reviewed journal unless you are using a tissue source that is already well characterized and reliable in their view, to begin moving away from that. That's actually something I'm happy to see in the federal government now, that it has a new fetal tissue advisory panel that's approving research that uses some existing fetal tissue, but also alternative sources to see if they can ultimately replace it. And so I think that the Catholic universities are in the lead of that in terms of finding new alternatives, actually promoting, again, scientific progress that is not ethically fraught. And in terms of the ethics of in vitro fertilization, experimentation on embryos that's harmful to them, and things of that sort, there's also going to be a difference, that they would not be pursuing that. But it's not the difference between pursuing science and having faith. It's a difference in where we put our priorities and how we advance science.
Okay, very good. Thank you. What about the issue of allocating genetic resources? Do you think the benefits of gene therapy will be shared equally with other nations?
I would love to think so. And of course, that's the dream. I'm thinking of where we are now, even without any widespread use of gene therapy. We are well on the way to tailoring treatments and even drugs to the genetic makeup of our patients. I've had a couple of surgeries of my own now that I'm in my 60s, and they were done in a way that was impossible only a few years ago, because there was just a tiny little incision that later completely disappeared. The surgery was done laparoscopically. That's a hard word to say. And meanwhile, people in the third world are suffering from malnutrition and the diseases that come from that. They have very, very few of the therapies we have that we even consider very basic. We have a very long way to go for even helping these nations to come up to the level of healthcare that we have. And so my fear is that gene editing, and particularly germline, adds another layer of discrimination or disparity to that. We're very far now from allowing everybody to have the same healthcare, so that you have a world of the genetic haves and the genetic have-nots that increases divisions and mistrust between nations. I think one of the reasons why the UN was so happy to talk about innate human dignity was precisely to say, our nations all have these diverse populations and diverse cultures, but we have to agree on the fact that we are all equal in something very basic, or we'll never be able to work together as an international organization. And that's true here as well. I think it is a goal that is very important, and we're very, very far away from it.
Okay. You seem to want to talk about the movie Gattaca. What do you find most appealing about the way the movie Gattaca presents these issues?
Well, I think it has many wonderful things. It's a very thoughtful movie. Brave New World is a wonderful dystopian vision and very scary, but most people would say, well, that'll never happen here because we're in a democratic society and everybody has their individual freedom. It's a beautiful representation of soft coercion because, couples they go to their doctor or the geneticist who says, you want to give your child the best possible start. And the more children get that best possible start, you are under pressure because you are allowing your child to start life as an inferior person, at one point they say second-class citizen or a new underclass. There's a character in the movie, I don't know if I should do spoilers, but there's a character in the movie who is genetically enhanced, who has had, well, as it turns out, it looks like he's had an accident. He was hit by a car, and now he's in a wheelchair, and he will never achieve the dreams for which he was genetically enhanced. It turns out that he was supposed to be the greatest swimmer who ever existed, and he competed in the Olympics, and he only got a silver medal, and he walked in front of the car because it was only a silver medal. And the expectations of everyone who's been enhanced in this way is so enormous that their expectations, even on themselves, become completely unrealistic. This person doesn't end well either. There's also a lovely scene where the character who is pretending to be genetically enhanced and has purchased this other person's genetically enhanced identity goes to a concert with his new girlfriend. And the pianist is just wonderful, playing a very classical piece. And at the end, the pianist gets up and throws his white gloves into the audience. It's like the Beatles, and he catches one of them, and he figured the glove has 6 fingers. And then he looks at the poster for the concert, and he realizes the pianist was genetically enhanced to have 6 fingers. And he says to his girlfriend, I didn't realize he had 6 fingers. And she says, that piece cannot be played without 6 fingers. So if you have 5 fingers and you want to be a great pianist, you can't play the modern compositions. So it's all kinds of ways in which, freedom, unlimited freedom to enhance and get enhanced turn out to have some perhaps unintended effects. The folks who are genetically enhanced don't even seem to be that happy with themselves because they're always competing against others and competing against what was expected of them. And in the end, the non-genetically enhanced person who is an impersonator, there are 3 people who know his background and who he really is, and they all let him get away with it because they've all had experiences of their own of not living up to their genetic enhancement. And they say, you go, show people that you are not limited by your genetic background, that the human spirit is still alive and can transcend what people thought of you.
Great. Sounds like a great movie. I need to watch that. Why don't we open it up to all 3 panelists and finish up the discussion. We have about 5 minutes before we're going to close it. And actually, there is one question here that just popped up, and any of you could answer it. There's a genetic link to alcohol dependence and possibly addiction, given the potential for selection of and removing or making this gene inactive. Would this, because of the greater societal benefit, be worth researching? And what are the ethics of parents to be choosing?
So there's there are some genetic differences that have been linked to susceptibility to addiction, different, alcohol or opioids or things like that. What hasn't been researched, as far as I know, this is not my area of particular specialty, is do those particular differences also then enhance other abilities in the person? Are there artistic sensibilities? Are there perceptive sensibilities? Are there other things that are enhanced by that particular genetic configuration, in spite of the fact that it gives one a higher susceptibility? And then, of course, you have to put that in the whole context of, does everybody who have that particular genetic configuration become addicted? And the probability is not. So then what environmental factors are also involved? So that's when you get into those, more complex genetic configurations and their interaction with the environment, then Tim was saying before how complex it is, just germline engineering with a particular monogenic, single gene disorder. These become incredibly complex.
Well, the other thing I would just add is it reminds me, it's less on target to the direct question, but the question illuminates it a little bit, which is when you kind of drill into people and say, well, just articulate what is the specific disease that you think can uniquely be unlocked through germline gene editing for clinical applications, where there's no viable alternatives. There's almost no list. People can come up with this. I mentioned this Russian science. Well, there's a rare form of deafness, but you got to do a lot of gymnastics to get there. So if you assume someday it could be safe, it could be effective, that you could run an ethical clinical trial, then you still get to but there are other legal approaches, whether it's IVF, whether it's gene therapy or gene editing of somatic cells and things like that appear as if they could be an alternative. So you got to do a lot of gymnastics, it strikes me, to get to a point where you would do something so groundbreaking. And I think it makes it really tricky.
Okay, thank you. I think I will turn it back over to Tom now. I appreciate your talk, Richard, and everybody else. So, Tom?
So, Tom, you're on mute.
Sorry about
there you
go. Sorry about the microphone. Okay. We need sort of a wrap-up, a summary, a perception of the whole picture. And for that, I'm going to call on our Associate Director of iTest, Sister Marianne Postiglione, who will bring us to the conclusion of the conference in a final prayer. Sister Marianne.
Okay, do I have to do anything? Oops. All right, here I am. Gosh, to sum up, something like this would be more than fearful for anyone. I'm not going to do what some of our media people do after conferences, and that is talk for a half hour about what was said. I think we can easily absorb that ourselves. But I do want, before I get into iTest, I want to thank our trinity of speakers as a little nod to theology, that since listening and watching, and these are, I would say, life by PowerPoint, rather than what some have called death by PowerPoint. We have a deeper understanding of the basics of genetic engineering, the development and advances worldwide of genetic engineering, and the moral, theological, and ethical ramifications of that. If you want to see the whole program again, that will be recorded. It's being recorded now, and it will be on our website. If I have a few moments, I just want to inject a little personal thing. I had a student at Salve Regina College, a brilliant, talented young woman who was of Greek extraction. She had sickle cell anemia. And from what I've understood from people who have watched her during a terrible attack, is that she would probably be willing to trade sickle cell anemia for malaria. Because that simply, if you have that sickle cell gene, usually you're immune to malaria. I'm sure that she would have been very happy to trade that one for the other. She died at age 35 when she had so much ahead of her. So I am all for CRISPR, and particularly the sickle cell anemia idea of disease. Now, just let me say a few words about iTest. Tom did a marvelous job introducing iTest. I don't have too much to add to that, other than to say that we want you to join us. We want you to go to our website, which is very easy to remember, www.faithscience.org, and go to our website. It's a marvelous piece of work. I didn't have anything to do with it, so I can say that. And of course, there will be the donate button, which now they're telling us in Crisis and Crooks magazine, just push on that, and it probably for the cost of a Starbucks coffee or latte, if you're into latte, we'd be happy to have any donation that you would feel free to give. Just to remind you that we do have also publish a monthly newsletter in addition to our quarterly journal or bulletin. And we thank Sheila Roth and Sebastian Mahfoud for putting together that thing that I've always wanted to have from iTest, a newsletter every month. If you want to be added to that, simply go to our iTest at archstl.org. All this will be on the screen for you too later on. However, I think it's important right now to thank Sheila Roth and Sebastian Mahfoud, particularly for the Yo Person work they've put into this production of the artistic brochure or flyer that they sent out. I understand after being with iTest for 33 years what a lot of that involves. And I'm happily into retirement, still as a consultant to iTest and as a senior editor of the Bulletin. Speaking of which, we produced or published an entire issue of the iTest Bulletin in 2019 of the fall. So it was a year ago. Everything in that issue was on CRISPR. So if any of you are interested in going back and doing some background reading, you can get that on our website. And I'm sure we'll be able to show you where that is. It's very easy to find bulletins on our website. Father Kevin Fitzgerald had 2 articles in that bulletin, one on human genetic engineering and then another with a co-author on the connection of genetic engineering and the viewpoint of Teilhard de Chardin, which I highly recommend. Tom Sheehan did a summary of that article, and then there's a link to the full article if you'd like to follow that. Finally, without further ado, I want to thank Sebastian, too, for his marvelous work on putting together the technical aspect of this. We know that, especially at a webinar, technology, which could at times be a tangled mess, and it could be, save for the expertise of Sebastian, he is unflappable under any circumstance, no matter what is happening. The ceiling, the sky could be falling in. Sebastian is there, unflappable. Finally, and most of all, thanks to our dauntless director, Tom Sheehan, our director since 2008, 2 years after Father Brungs died, our director, who facilitates these webinars seamlessly and with a sure hand and leads iTest and its members through the sometimes thorny path of faith and science. And we thank you, Tom, for that. And I've been elected to do the final prayer because Tom Davis is off trying to save his wife from terrible things with cars. So what I've chosen was just a short reflection that Father Brungs did a number of years ago, 2000 in fact, on the whole meaning of the body in science and in our salvation. And instead of a prayer, I'd like to just read these 2 short paragraphs, if we have the time, on a reflection on what we are in the body and human dignity. We are all searchers of the truth. We can never say that we have arrived at our destination, which is the truth, until we see him face to face. Gregory of Nyssa uses an image of a spiral. Seeing him, we will begin to know him, and knowing him better, we will love him more, and loving him more, we will know him better in an ascending spiral forever. What a breathtaking thought. But we will know him as a human being with a body, always with a body, as we are bodied. His body and ours in a never-ending dance of love. Our bodies will know him better and love him more, and his body will be in union with ours. Amen.
Okay, thank you very much, Sister Marianne. This brings our conference to a close. We absolutely want to thank our wonderful speakers, not only for individual excellent presentations, but for coordinating them so well to turn it into a complete, entire presentation, a whole unity. We want to thank all of you who are attending today. This webinar will be posted on our website in the coming weeks, as soon as we clean up a few glitches. We hope to have you with us again at another webinar sometime in the reasonably near future. To learn about such plans, webinars coming up, and other things, and to keep abreast of iTest, other programs and activities, we ask you to regularly visit our iTest website. And again, that's at www.faithscience.org. And finally, to receive the most up-to-date and information and to stay really connected with all of iTest benefits, we encourage you to join iTest. Again, thank you very much, and good evening.
Thank you for listening to a production of WCAT Radio. Please join us in our mission of evangelization. And don't forget, love lifts up when knowledge takes flight.